There's something breathtakingly humbling about staring up at the night sky, realizing just how small we are in the grand scheme of the universe. But what if I told you that some of the most mind-bending cosmic mysteries aren't even in our own galaxy? Just beyond the edges of the Milky Way, a strange and chaotic neighbor dances in the darkness, the Large Magellanic Cloud. This dwarf galaxy, a satellite of our own, is a treasure trove of cosmic oddities where the laws of physics seem to twist into the surreal. From rogue black holes racing through star clusters to ghostly nebulae that glow with no clear source of light, the LMC defies explanation at every turn. Imagine a place where stars vanish without a trace, where cosmic explosions leave behind more questions than answers, and where entire regions of space pulse with energy we can't yet understand. This isn't science fiction, it's happening right now, 160,000 light-years away. The Large Magellanic Cloud is a laboratory of the bizarre, a cosmic playground where nature conducts experiments we're only beginning to decode. And the deeper we look, the stranger it gets. Some of these phenomena challenge everything we think we know about how the universe works, like a celestial whisper hinting at secrets we've yet to uncover. So why does this matter to us here on Earth? Because every mystery in the LMC is a clue, a piece of the puzzle that could reshape our understanding of reality itself. Over the next few minutes, we're going to journey into the heart of this enigmatic galaxy, exploring 50 of its most astonishing and unexplained phenomena. Some will leave you in awe, others might send a chill down your spine, but one thing's for certain: by the end, you'll never look at the night sky the same way again. The universe is stranger than we can imagine, and the Large Magellanic Cloud is proof. Let's dive in. The first stop on our journey through the Large Magellanic Cloud's strangest phenomena takes us to a place so bright it outshines entire galaxies. Meet the Tarantula Nebula, a sprawling cosmic web of gas and dust where stars are born at a rate that puts the rest of the local universe to shame. Officially known as 30 Doradus, this nebula isn't just another stellar nursery. It's a monster, blazing with the light of millions of stars crammed into a space just 1,000 light-years across. To put that in perspective, if you plop the Tarantula Nebula where the Orion Nebula sits in our own galaxy, it would cast shadows on Earth at night. But here's what really baffles astronomers: its brightness shouldn't make sense. Nebulae typically glow because of the stars inside them, but the tarantula's radiance goes beyond what even its dense population of massive stars can explain. Some of these young stellar giants weigh in at over 200 times the mass of our Sun, burning so fiercely they live fast and die spectacularly. Scientists suspect hypernova explosions 10 times more powerful than supernova might be at play here, tearing through the nebula and pumping energy into the surrounding gas. Others think there could be hidden stellar behemoths buried deep in the dust, or even runaway collisions between stars, creating temporary flashes of unimaginable brightness. Then there's the sheer scale of star formation happening here. While our Milky Way might produce a handful of new stars each year, the Tarantula Nebula cranks them out by the dozens. It's like comparing a quiet countryside pond to a roaring waterfall. Both have water, but one is an unstoppable torrent. Some researchers believe this frenzy is fueled by the LMC's turbulent past, with gravitational interactions between galaxies funneling massive amounts of gas into this one explosive region. Whatever the reason, the Tarantula Nebula stands as a cosmic rebel, breaking every rule we thought we knew about how nebulae behave. And tucked within its glowing tendrils, there might be clues about the universe's most violent and energetic events waiting to be uncovered. Just a stone's throw away from the dazzling chaos of the Tarantula Nebula lies another cosmic head-scratcher, N44, 1,000 light-year-wide superbubble that looks like the universe took a giant bite out of the galaxy. Picture a soap bubble floating in space, except instead of soap, it's made of scorching hot gas, and instead of floating peacefully, it's expanding violently, carving out a cavernous void in the surrounding starscape. What makes N44 so perplexing is that nobody's entirely sure how it formed in the first place. Superbubbles usually grow from a combination of stellar winds, and supernova explosions imagine giant stars blasting out gusts of charged particles like cosmic hurricanes, only to eventually explode and punch even bigger holes in space. But N44's sheer size and the energy required to create it don't quite add up. Sure, there are young, massive stars inside it that could be contributing, but astronomers have run the numbers and their combined power falls short of explaining this colossal cavity. Then there's the eerie quiet at its heart. Unlike other superbubbles, which are often crammed with the remnants of dead stars, N44's center is strangely empty, as if something swept it clean. One theory suggests a chain reaction of supernova went off like dominoes, their shockwaves merging into a single, gargantuan push that blew out the gas like a cosmic exhale. Others speculate that something more exotic might be at play, perhaps a runaway black hole plowing through the region, or even the remnants of an ancient, cataclysmic collision between stars we can't even imagine. But here's the real kicker: N44 isn't just a static hole in space. It's still evolving, still growing. The walls of the bubble glow with fierce ultraviolet light, heated by the very stars that might have created it, while inside, temperatures reach millions of degrees. If you could float in the middle of it and survive the radiation, you'd be surrounded by a shimmering, turbulent ocean of gas, stretching farther than the human mind can easily grasp. This isn't just a curiosity, it's a cosmic laboratory. By studying how N44 behaves, astronomers can piece together how energy moves through galaxies, how star formation reshapes its surroundings, and maybe even uncover hidden forces we don't yet understand. Because if there's one thing the Large Magellanic Cloud loves to do, it's take the rulebook of astrophysics and toss it straight into the cosmic winds. And N44, it's just getting started. Now let's turn our attention to one of the most unpredictable cosmic fugitives in the Large Magellanic Cloud, HD 5980, a runaway star with a flair for the dramatic. This isn't just any fast-moving star. It's a hypervelocity beast racing through space at speeds that defy logic, as if it were hurled from some celestial slingshot. But what really sets HD 5980 apart isn't just its speed. It's the star's shocking history of violent outbursts, including a legendary eruption in 1994 that briefly outshone its entire host cluster, mimicking the fury of a supernova while somehow surviving the spectacle. Most stars live relatively quiet lives, but HD 5980 behaves more like a cosmic rebel with a death wish. Classified as a luminous blue variable, a rare, unstable type of star prone to extreme mood swings, it's one of the most massive and luminous stars known, burning so fiercely it's practically tearing itself apart. The 1994 event wasn't just a flare-up, it was a full-blown explosion, ejecting enough material to form several planets, all while the star itself somehow clung to existence. Astronomers still debate what triggered it. Some point to internal instabilities, while others suspect a catastrophic interaction with a companion star, like a stellar duel gone wrong. Then there's the mystery of its escape velocity. HD 5980 isn't just drifting, it's flying through the LMC at hundreds of kilometers per second, faster than most stars ever achieve. Normally, stars reach these speeds through close encounters with supermassive black holes or explosive stellar breakups, but HD 5980's neighborhood lacks the usual suspects. That's led to wilder theories, like the possibility of a dark matter kick, an invisible, concentrated clump of dark matter giving the star a gravitational shove we can't see. Others propose it was once part of a tight-knit binary system that went supernova, flinging it outward like a cosmic catapult. What makes this star so fascinating isn't just its past antics, but what it might do next. Luminous blue variables are ticking time bombs, often ending their lives in supernova or even hypernova. And given HD 5980's track record, astronomers are watching it like a hawk waiting for the next eruption. Will it finally self-destruct in a blaze of glory, or will it defy expectations again, leaving us with more questions than answers? Either way, this runaway star is a reminder that the universe doesn't play by the rules, and the Large Magellanic Cloud is its wildest playground. Among the twisted remnants of dead stars littering the Large Magellanic Cloud, one stands out for its eerie perfection, SNR 0509-67.5. This supernova remnant isn't just another cosmic wreck, it's a flawless, glowing sphere, as if some celestial sculptor took a chisel to the universe and carved a bubble of pure energy. Most stellar explosions leave behind chaotic, jagged debris fields, but this one defies expectations with its near-mathematical symmetry, stretching over 23 light-years in every direction with uncanny precision. What makes this ghostly shell so baffling is how it contradicts everything we know about the violent deaths of stars. Supernova are nature's most destructive forces, titanic explosions that tear stars apart with unimaginable fury, sending shockwaves rippling through space in all directions. Yet instead of the expected mess of tangled filaments and uneven debris, SNR 0509-67.5 presents a smooth, unbroken surface, like a soap bubble frozen mid-pop. The secret to its perfection lies in its origins. This remnant is the aftermath of a Type Ia supernova, a specific kind of explosion that occurs when a white dwarf star steals too much material from a companion, crossing a critical mass threshold and detonating in a thermonuclear fireball. Unlike the messy collapses of massive stars, Type Ia supernova detonate with startling uniformity, their energy radiating outward in a near-perfect sphere. But even among these orderly explosions, SNR 0509-67.5 is an outlier. Most Type Ia remnants still show some irregularities, knots of gas, asymmetrical bulges hinting at turbulence during the blast. This one, flawless, astronomers have pieced together a chilling timeline. Roughly 400 years ago from our perspective, light from this supernova finally reached Earth. Telescopes later spotted its remnant, and by studying the glow of its shock-heated gas, they confirmed something extraordinary. The explosion's energy must have been distributed with near-perfect balance, like a bomb detonated with impossible precision. Some theories suggest the white dwarf was spinning at just the right speed to smooth out irregularities, while others propose an exotic double detonation scenario where twin waves of nuclear fire race through the star in perfect sync. But the real mystery isn't just how it formed, it's what surrounds it. The shell floats in near isolation with no obvious stellar companion left behind. If the white dwarf did steal matter from a neighboring star, where did that star go? Was it utterly annihilated in the blast or flung away into the darkness? The absence of clues only deepens the enigma. Peering into this cosmic bubble is like staring into a frozen moment of destruction, preserved with unnatural elegance. It challenges our assumptions about how stars die, forcing us to reconsider the fine balance between chaos and order in the universe. And somewhere in its glowing embrace, there might be answers hidden in the light of a supernova that refused to leave anything to chance. The Large Magellanic Cloud isn't just defying expectations with its visible oddities, it's also hiding an invisible secret that could upend our understanding of the cosmos. Most dwarf galaxies like the LMC are thought to be cocooned in massive halos of dark matter, an unseen gravitational glue that keeps them intact. But here's the twist: mounting evidence suggests the LMC might be missing this shadowy scaffolding entirely. It's as if we've stumbled upon a cosmic rule-breaker, a galaxy that somehow thrives without the very thing we thought held all galaxies together. This anomaly first caught scientists' attention when they studied the motions of stars and gas clouds within the LMC. In a typical dwarf galaxy, these objects orbit much faster than visible matter alone can explain, a telltale sign of dark matter's gravitational pull. Yet the LMC's rotation curve, the graph-plotting stellar speeds against distance from its center, doesn't show the expected spike. Instead, it flattens out as if the galaxy's gravity comes almost entirely from the stars and gas we can see. Some measurements even suggest the LMC's total mass is startlingly close to its visible mass, leaving little room for dark matter's usual dominance. The implications are staggering. The Lambda CDM model, our leading framework for how the universe structures itself, relies on dark matter as the hidden architect of galaxy formation. Without it, dwarf galaxies shouldn't hold their shape, yet the LMC isn't just holding together. It's one of the most vibrant and star-forming galaxies in our cosmic neighborhood. Could this mean the LMC is an exception, perhaps stripped of its dark matter by past collisions? Or does it hint at something more radical, that our theories need rewriting? One compelling alternative is modified Newtonian dynamics, or MUND, a hypothesis suggesting gravity behaves differently at galactic scales than Newton or Einstein predicted. In this view, the extra gravitational kick we attribute to dark matter might actually be a quirk of gravity itself, stronger where matter is sparse. The LMC's puzzling dynamics fit suspiciously well with some MUND predictions, fueling debates about whether we've been misinterpreting the universe's scaffolding all along. Then there's the cosmic context. The LMC isn't floating alone, it's locked in a gravitational dance with the Milky Way, trailing streams of stars and gas as it circles us. Some simulations suggest our galaxy's gravity could have ripped away the LMC's dark matter over billions of years, leaving it naked. But if that's true, why doesn't every satellite galaxy show the same stripped-down profile? And why does the LMC still sport such a robust structure? The mystery deepens when we compare it to other dwarfs. Take the ultra-faint galaxies orbiting the Milky Way. These dim, ancient systems are practically drowning in dark matter, with mass-to-light ratios hundreds of times higher than the LMC's. If dark matter is universal, why does one neighbor hoard it while another seems to lack it entirely? Every observation adds layers to the puzzle. Recent studies of the LMC's outer edges reveal tantalizing hints of a faint, extended halo, perhaps the ghostly remnants of a dark matter cloak that's been mostly torn away. Other teams argue the data's been misinterpreted, and the LMC's dark matter is simply hiding in plain sight, distributed differently than models predict. What's clear is that the LMC isn't just a curiosity, it's a testbed for fundamental physics. Whether it challenges dark matter theory, supports alternative gravity, or reveals some unseen galactic evolution process, this cosmic rebel is forcing us to rethink the invisible foundations of the universe. And the more we study it, the clearer it becomes. The Large Magellanic Cloud doesn't follow the rules, it writes its own. Among the fiery debris of exploded stars in the Large Magellanic Cloud, two supernova remnants stand out not just for their violence but for the cosmic fingerprints they've left behind, N132d and N49. These twin titans of destruction share eerie similarities, from their unusual chemical makeup to their jagged, sprawling shapes, yet each tells a wildly different story about how stars meet their end. Take N132d first, a sprawling, claw-like nebula that glows with the unmistakable signature of oxygen and neon. These elements are the calling cards of a massive star's final act, forged in its core and then blasted into space when it exploded. But what's strange here is how unevenly those elements are scattered. Instead of a uniform cloud, N132d looks like a cosmic hand reached in and stirred the debris, leaving swirls and knots of gas that defy the neat, spherical remnants we often see. Astronomers think this chaos might be evidence of a turbulent death. Perhaps the original star was spinning wildly as it blew apart, or maybe the explosion itself was lopsided, sending shockwaves barreling through space in one direction more forcefully than others. Then there's N49, a remnant so bizarre it practically rewrites the textbook on stellar explosions. At first glance, it shares traits with N132d, same oxygen neon glow, same sprawling asymmetry, but buried deep in its wreckage lies something extraordinary, a magnetar. This ultra-dense, rapidly spinning neutron star packs a magnetic field a quadrillion times stronger than Earth's, spinning like a furious top and sending pulses of X-rays screaming across the cosmos. Magnetars are already rare, but finding one nestled inside N49 raises burning questions. Did the original star's collapse trigger some freakish magnetic amplification? Or was this remnant born from a collision, two stellar corpses merging in a cataclysm so violent it birthed a magnetic monster? The contrasts don't stop there. While N132d's light echoes faint ripples of illumination bouncing off interstellar dust hint at a single, definitive explosion, N49's surroundings suggest multiple waves of destruction, as if the star didn't just die once but in fits and starts. Some researchers speculate that N49's progenitor might have been part of a binary system, its death throes complicated by a companion star's gravitational tug-of-war. Others point to the remnant's bizarre bar structure, a dense lane of gas slicing through its center like a cosmic scar, as evidence of an explosion channeled by magnetic fields we can barely comprehend. What binds these two remnants together, though, is the sheer unpredictability of their aftermath. Supernova are nature's ultimate fireworks, yet the debris they leave behind twisted, asymmetrical, littered with extreme objects like magnetars feels less like a tidy conclusion and more like a cosmic question mark. If there's a lesson here, it's that even in death, stars refuse to follow a script, and in the Large Magellanic Cloud, where the rules seem made to be broken, N132d and N49 are perfect examples of chaos turned into art. Deep in the heart of the Tarantula Nebula, where star formation runs wild, lies a cosmic gladiator arena, the R136 star cluster. This dense gathering of stellar titans isn't just impressive, it's home to some of the most extreme stars ever discovered, including the heavyweight champion of the known universe, R13601. Picture a star so colossal it makes our sun look like a speck of dust, a searing, blue-hued monster weighing in at over 250 times the mass of our own star, blazing with the brightness of nearly 9 million suns combined. Stars like R13601 shouldn't exist, at least not according to our current understanding of how stars form. For decades, astrophysicists believed there was a hard limit to stellar size around 150 solar masses because the intense radiation pressure from such massive objects would blow away the very gas clouds needed to feed their growth. Yet here's R13601 laughing in the face of that limit, forcing scientists to reconsider how stars can grow so unimaginably large. One theory suggests these behemoths might form through violent stellar mergers, young, massive stars in densely packed clusters colliding and merging like cosmic snowballs growing ever larger. Others propose that the extreme conditions in the Tarantula Nebula, with its thick, turbulent gas clouds, allow stars to keep gobbling up material even as they radiate fierce energy. But the truth is, nobody knows for sure. R13601 is a living paradox, a star that shouldn't be, and its very existence is rewriting astrophysics textbooks. Then there's the star's impact on the cosmos itself. Stars this massive don't just burn, they flood their surroundings with enough ultraviolet radiation to ionize hydrogen atoms, stripping away electrons in vast bubbles around them. This process, called reionization, played a crucial role in shaping the early universe, clearing the cosmic fog left over from the Big Bang and making the universe transparent to light. R13601 offers a glimpse into that ancient era, a nearby laboratory for studying how the first stars, likely just as massive, transformed the infancy of space. But here's the catch: these monsters live fast and die young. While a star like our Sun will shine steadily for billions of years, R13601 is burning through its fuel at a breakneck pace, destined to explode in a hypernova within a few million years, a cataclysm so powerful it could outshine entire galaxies. When it does, it won't just leave behind a neutron star or black hole. It might completely disintegrate, its core collapsing so violently that it produces a torrent of gamma rays capable of sterilizing nearby planetary systems. Yet even in death, R13601 and its cluster mate serve a purpose. The heavy elements forged in their cores, oxygen, carbon, neon, will be blasted across space, seeding future generations of stars and planets. We're literally made of stardust, and stars like this are the universe's ultimate factories, producing the building blocks of life itself. The R136 cluster isn't just a curiosity, it's a cosmic time capsule, a window into both the universe's violent past and its turbulent future. Every observation peels back another layer of mystery, challenging what we thought we knew about star formation, stellar evolution, and the forces that shape the cosmos. And as long as stars like R13601 keep defying expectations, the Large Magellanic Cloud will remain one of the most thrilling enigmas in the night sky. Most galaxies have a predictable structure, spiral arms winding around a bright core, or maybe a smooth elliptical glow, but the Large Magellanic Cloud, it's the cosmic equivalent of a bent paperclip. At its heart lies a mangled, twisted bar, a dense lane of stars that should be straight, yet looks like it's been tugged and warped by invisible hands. This isn't just a visual oddity, it's a glaring sign that the LMC has been through the gravitational wringer, its very shape stretched and scrambled by a billion-year tug of war with its neighbors. The culprit, a celestial game of pull and twist between the Milky Way and the LMC's smaller sibling, the Small Magellanic Cloud. Every time these galaxies swing past each other, their gravity acts like a cosmic whirlpool, distorting the LMC's bar like taffy. Recent simulations suggest the Small Magellanic Cloud might be the main instigator. Its last close pass, around 1.5 billion years ago, could have yanked the bar sideways, leaving it permanently crooked. But the Milky Way isn't innocent either. Our galaxy's immense gravity acts like an anchor, slowly twisting the LMC's structure over eons, warping its core into this bizarre, off-kilter shape. What's fascinating isn't just the bar's contorted appearance, but what it reveals about galactic survival. Bars are engines of star formation, funneling gas inward and sparking new stellar births. Normally, they're stable, symmetrical, efficient cosmic conveyor belts, but the LMC's bar is a chaotic mess, and yet it's still working. Somehow, despite the gravitational turmoil, gas squeezes through its twisted lanes, igniting star-forming regions where it shouldn't be possible. This challenges the assumption that barred galaxies need orderly structures to thrive. The LMC's bar is proof that even in chaos, galaxies find a way. Then there's the bigger picture. The warped bar is a snapshot of galactic evolution in action. Astronomers used to think dwarf galaxies like the LMC were simple, static systems. But this distortion tells a different story. They're dynamic, reshaped by encounters, their histories written in the bends and kinks of their stars. If we can decode the bar's wrinkles, we might uncover secrets about the Milky Way's own past collisions, or even predict the LMC's fate. Because one thing's certain, this isn't the last time its structure will be rewritten. Every galactic close encounter leaves a mark, and the LMC's bar is just the latest chapter in a saga of cosmic tug-of-war. Hidden in the star-studded tapestry of the Large Magellanic Cloud, there's a cosmic storm raging, one that defies the usual rules of black hole behavior. Meet LMC X3, a microquasar so energetic it mimics the violence of distant quasars billions of times larger, all packed into a system barely 30 light-years across. At its heart lies a black hole roughly 10 times the mass of our Sun, locked in a lethal dance with a companion star. But here's what makes this duo extraordinary. It's not just devouring matter. It's spitting it back out at nearly the speed of light, creating jets so powerful they glow in X-rays across interstellar space. What baffles scientists isn't just the existence of these jets, but their wild unpredictability. Normally, accretion disks, the swirling maelstroms of superheated gas around black holes, behave like orderly whirlpools, funneling material inward with some semblance of rhythm. LMC X3's disk, however, is a rebel. It flickers erratically, its X-ray output swinging by factors of hundreds in mere days, as if something inside the system keeps yanking the cosmic plug. Some observations even show the jets changing direction abruptly, like a fire hose with a mind of its own. This chaos might stem from the black hole's gluttonous companion, a massive blue supergiant star dumping material onto its dark partner far faster than the disk can handle. Imagine trying to drink from a fire hydrant. The overflow has to go somewhere, and in LMC X3's case, it gets blasted into space as those relativistic jets. But there's another twist: the black hole's spin. Measurements suggest it's rotating at nearly the maximum possible speed, turning space-time itself into a twisted funnel that could be flinging those jets off course. The real shocker: this tiny system mirrors the behavior of quasars, supermassive black holes at the centers of galaxies, whose jets can span millions of light years. How does a black hole barely heavier than a star replicate the fireworks of cosmic behemoths millions of times its size? The answer might lie in scale. Microquasars like LMC X3 are essentially miniature versions of their gigantic cousins, operating under the same physics but on a compressed timeline. That makes them perfect laboratories. Their rapid changes let us observe in decades what would take quasars millennia, offering clues about how all black holes feed, spin, and unleash their fury. Yet mysteries remain. Why does LMC X3's accretion disk sometimes vanish entirely, only to reboot weeks later? Could magnetic fields, tangled like cosmic spaghetti near the black hole's event horizon, be behind the jet's erratic wobbles? And what happens if the companion star finally runs out of fuel? Will the system go silent or erupt in one final, spectacular outburst? Every flicker of X-rays from this microquasar is a message in a bottle, tossed across 160,000 light-years, and decoding it could rewrite how we understand not just black holes, but the very fabric of high-energy physics. After all, when even the smallest monsters in the universe can outshine galaxies, it's a reminder: size isn't everything. Chaos packs a punch. The outskirts of the Large Magellanic Cloud hold a ghostly secret, a sprawling river of ancient stars winding through the darkness like a cosmic fossil. This stellar stream, a delicate filament of aging suns drifting along the LMC's fringes, isn't just another collection of stars. It's a celestial crime scene, a relic from what might be one of the LMC's most violent acts: the cannibalization of a smaller dwarf galaxy billions of years ago. What makes this stream so puzzling isn't just its existence, but the stars themselves. They're shockingly primitive metal, poor to the extreme, with compositions suggesting they formed when the universe was still in its infancy. Unlike the LMC's bustling star-forming regions, these ancient suns carry the chemical fingerprints of a time before heavy elements like iron and carbon were common, making them closer in composition to the universe's first stars than to most of their LMC neighbors. That disparity is the first clue to their origins. If these stars belonged to the LMC from birth, they'd have been enriched by later generations of supernova. The fact that they weren't hints they came from somewhere else, a smaller, more primordial galaxy torn apart and absorbed long ago. Then there's the stream's path. Unlike the orderly orbits of stars born in the LMC, this ribbon of suns traces a chaotic, looping trajectory, as if still reeling from the gravitational turmoil of its absorption. Simulations suggest the original dwarf galaxy might have been stretched into this elongated stream over billions of years, its stars gradually scattering like breadcrumbs along the LMC's gravitational wake. But here's where it gets strange. The stream's stars aren't just old, they're also bizarrely isolated. Most tidal streams are eventually mixed into their host galaxy's halo, but this one lingers, preserved in startling clarity. Some astronomers think the LMC's unique gravitational environment, less disruptive than larger galaxies like the Milky Way, might have left the stream eerily intact, like a fossil frozen in cosmic amber. The implications ripple far beyond the LMC. If this stream truly is the remains of a devoured dwarf, it means the LMC wasn't always the hunter, it was once the prey. Before being captured by the Milky Way's gravity, it might have had its own miniature satellite system, a family of smaller galaxies it gradually consumed. That reshapes our understanding of galactic evolution, suggesting even dwarf galaxies engage in celestial cannibalism, building themselves up by tearing their neighbors apart. But the biggest question remains, why is this stream so metal-poor? One theory points to the original dwarf's isolation. Perhaps it formed in a near-pristine pocket of the early universe, far from the polluting explosions of early supernova. Another possibility is even more intriguing. The stream might contain stars from the universe's first generation, celestial elders so ancient they predate the creation of most heavy elements altogether. Finding even a handful of these legendary population Roman III stars, theoretical pioneers of cosmic dawn, would revolutionize our understanding of stellar evolution. Every observation adds layers to the mystery. The stream's stars aren't just passively drifting, some show subtle chemical variations, as if they're the mangled remnants of multiple smaller systems swallowed in succession. Others cluster in unexpected ways, hinting at pockets of resistance, regions where the original dwarf's core might have held together longer before finally dissolving. This isn't just an archaeological curiosity, it's a window into the LMC's hidden past, a reminder that even the smallest galaxies have violent histories. And as astronomers piece together the story written in these ancient stars, one thing becomes clear. The universe doesn't just build galaxies, it forges them in collisions, tears them apart, and stitches them back together. The LMC's fossil stream is proof that no cosmic structure, no matter how small, escapes the drama of gravity's endless tug of war. While most stellar explosions are one-time cosmic spectacles, why Doradus is the universe's version of a repeating firework, a binary system that erupts in violent thermonuclear explosions not once but over and over again. Nestled in the Large Magellanic Cloud, this cataclysmic variable star consists of a white dwarf locked in a deadly embrace with a bloated, sun-like companion. What makes this pair so extraordinary isn't just their recurring eruptions, it's the sheer ferocity of each blast, defying predictions and leaving astronomers scrambling to understand why this particular nova refuses to play by the rules. The drama begins with the white dwarf's relentless gravity, siphoning hydrogen-rich gas from its companion star. As this stolen material accumulates on the white dwarf's surface, pressure and heat build until, like a powder keg igniting, the entire layer detonates in a runaway thermonuclear explosion. This is the classic nova cycle, a process seen in similar systems across the universe. But why Doradus takes it to the extreme? Most nova release energy equivalent to 100,000 suns. Why Doradus's eruptions blast out with the power of millions, outshining its entire host galaxy for weeks. What's baffling is the frequency and intensity of these explosions. Typical recurrent nova might flare every few decades, but why Doradus erupts roughly every 18 years? An unusually short gap that suggests it's guzzling material from its companion at an unsustainable rate. Even stranger, spectroscopic analysis reveals each eruption flings far more material into space than models predict. Some theories suggest the white dwarf could be spinning so fast it slingshots debris outward, amplifying the explosion's reach. Others propose magnetic fields channel the blast into focused jets like a cosmic blowtorch. Then there's the mystery beneath the surface. Most white dwarfs in nova systems hover near the Chandrasekhar limit, the maximum mass before they collapse into neutron stars. But why Doradus's white dwarf might be stuck in a precarious balancing act, repeatedly skirting that threshold as it gorges on stellar material? If so, each eruption isn't just a flashy light show. It's a desperate purge to avoid total annihilation. One day, this system might not stop at a nova. It could go supernova, tearing itself apart in a final, apocalyptic blast. Yet the most tantalizing question isn't why Doradus erupts, it's why. The Large Magellanic Cloud's low metallicity means its stars contain fewer heavy elements, which should theoretically make nova less energetic. Yet here's why Doradus erupting with unparalleled violence. Could its environment play a role, or does this system harbor some hidden quirk we've yet to uncover? Every eruption peels back another layer of the mystery, reminding us that even well-studied cosmic phenomena can still surprise us. And in a galaxy already packed with oddities, why Doradus stands out as a ticking time bomb, one that refuses to fade quietly into the dark. Globular clusters are supposed to be galactic staples, dense, ancient balls of stars that orbit galaxies like loyal cosmic sentinels. Our Milky Way has about 150 of them, each containing hundreds of thousands to millions of stars crammed into a tight sphere. But when we look at the Large Magellanic Cloud, something doesn't add up. For its size, the LMC should host dozens of these stellar relics, yet astronomers have only found a handful. It's as if someone raided the galaxy's treasure trove of globular clusters, leaving behind just a scattered few. The discrepancy is hard to ignore. Dwarf galaxies like the LMC typically form globular clusters at a rate proportional to their mass, meaning the LMC's current count is suspiciously low. Where did they go? One compelling theory points to gravitational robbery. The Milky Way's immense tidal forces may have plucked clusters from the LMC over billions of years, flinging them into intergalactic space or assimilating them into our own galaxy's halo. Evidence for this comes from the Magellanic Stream, a vast ribbon of gas and stars torn from both Magellanic Clouds as they orbit the Milky Way. If gas and stars were stripped away, why not globular clusters too? Some researchers speculate that a few of the Milky Way's outer halo clusters might actually be refugees from the LMC, captured during a close pass, but tidal stripping isn't the only suspect. The LMC's turbulent history of star formation might have suppressed globular cluster birth in the first place. These clusters form best in calm, metal-poor environments, conditions common in the early universe but rare in the LMC, which has undergone repeated bursts of violent star birth. Each wave of supernova would have heated and dispersed the gas needed to forge new globulars, leaving the galaxy with fewer of these ancient stellar fossils than expected. Then there's the twist. The clusters the LMC does have aren't behaving normally. Take NGC 1866, one of its largest surviving globulars. Unlike the Milky Way's ancient metal-poor clusters, NGC 1866 is relatively young and metal-rich, suggesting it formed during a later epoch of the LMC's chaotic star-forming history. This raises an even bigger question. Did the LMC ever have a classic population of old globulars, or has its disruptive environment always favored younger, stranger clusters? The mystery deepens when we compare the LMC to its sibling, the Small Magellanic Cloud. Despite being smaller and less massive, the SMC has roughly the same number of globular clusters, defying expectations. Could the LMC's missing clusters be hiding in plain sight, camouflaged by the galaxy's bright star-forming regions? Or did something uniquely destructive happen in the LMC's past, a collision, perhaps, or a near miss with another galaxy that scattered its globulars like marbles across the cosmos? Whatever the explanation, this isn't just a bookkeeping problem. Globular clusters are time capsules holding clues about galactic formation in the early universe. If the LMC truly lost most of its clusters, that upheaval would have reshaped its entire evolution. and if they never formed to begin with, it challenges our assumptions about how dwarf galaxies grow and change. The absence of these stellar relics might be the most telling clue of all, a silent witness to the LMC's violent, unpredictable past. Amid the chaotic beauty of the Large Magellanic Cloud, a peculiar gathering of stars stands out not for their size or brightness, but for their sheer defiance of expectations. Astronomers call it the blue blob, a compact swarm of young, intensely blue stars that seem to have no business being where they are. These aren't just ordinary stars, they're stellar misfits, blazing with the heat of newborn suns, yet strangely isolated from any known star-forming region. The question isn't just how they got there, it's whether they formed in place against all odds or were violently flung across space like celestial outcasts. The mystery begins with their color. Blue stars are the universe's short-lived powerhouses, burning so fiercely they exhaust their fuel in mere millions of years. Normally, we find them nestled in the heart of active stellar nurseries, surrounded by the gas and dust that birthed them. But the blue blob stars are adrift in relative emptiness, far from the Tarantula Nebula's frenetic star factories or any other obvious birthplace. Their isolation suggests one of two scenarios: either this patch of space somehow conjured stars out of thin gas long after its neighbors quieted down, or these stars were ejected from their home cluster at speeds that would make a comet blush. The ejection theory holds tantalizing clues. In dense star clusters, gravitational encounters between massive stars can act like cosmic slingshots, hurling some members into the void at staggering velocities. Imagine a game of stellar pinball where close passes between stars fling one another into oblivion. If the blue blob stars were born in a now dissolved cluster, their shared motion and similar ages would make sense. But here's the catch: they're not moving fast enough to support this idea. Runaway stars typically race through space at hundreds of kilometers per second, leaving clear trails. The blue blob stars, while unmoored, drift at more leisurely speeds, as if they've always belonged right where they are. That leaves the even weirder possibility: in situ formation. Could a wisp of gas, too faint for our telescopes to detect, have lingered in this quiet corner of the LMC, quietly coalescing into stars long after the galaxy's prime era of star birth? It's not impossible. Star formation is messy, and pockets of gas can survive surprisingly long in isolation. But triggering that collapse usually requires a shockwave, a nearby supernova perhaps, or a galactic collision. Neither fits neatly here. The blob stars show no chemical signs of supernova enrichment, and their surroundings bear no scars of recent upheaval. Then there's the blob's shape, not a symmetrical sphere like most clusters, but a ragged, elongated clump, as if something stretched it halfway across space. Some simulations suggest tidal forces from the LMC's bar could have pulled a once-tight group apart over eons, leaving this ghostly imprint. Others wonder if we're seeing the frayed edges of a much larger structure, most of its stars already scattered beyond recognition. But the real puzzle isn't just the blue blob's past, it's its future. These stars are doomed to die young, their brilliant blue hues a prelude to spectacular supernova. When they do, will they leave behind a void, or might their explosions trigger yet another wave of star birth in this seemingly barren patch of sky? Every observation adds layers to the riddle, reminding us that even in a galaxy as studied as the LMC, the universe loves to hide its most tantalizing secrets in plain sight. In February 1987, the night sky suddenly gained a brilliant new star, one visible to the naked eye despite being 160,000 light-years away. Supernova 1987 wasn't just the closest stellar explosion witnessed in modern times. It was a cosmic Rosetta Stone, offering scientists an unprecedented front-row seat to the violent death of a massive star. But decades later, this cataclysm still guards jaw-dropping secrets, starting with its bizarre, lopsided debris field and the baffling absence of the compact object it should have left behind. The first clue that something was unusual came from the supernova's iconic triple-ring structure. Most stellar explosions leave behind chaotic, asymmetrical wreckage, but SN 1987A's ejector formed a stunning hourglass shape, with two outer rings flanking a central equatorial belt like a cosmic bullseye. Even stranger, these rings weren't evenly distributed. The southern half of the debris field glowed significantly brighter than the northern side, as if the explosion had a preferred direction. Hubble Space Telescope images later revealed the culprit, the progenitor star, a blue supergiant named Sanjalik -69202, hadn't been perfectly round. Instead, it was likely shaped like a spinning top, its equator bulging outward from rapid rotation. When it exploded, this asymmetry imprinted itself on the blast wave, funneling more material and energy southward like a cosmic tilt. But the real mystery lies at the heart of the wreckage. Every core collapse supernova, the kind SN 1987 was supposed to be, leaves behind either a neutron star or a black hole, the dense corpse of the original star's core. Yet despite decades of searching with every telescope from radio to X-ray, astronomers can't find any trace of this expected remnant. The leading theory suggests a neutron star did form, but it's shrouded by so much debris that its light can't escape. Supporting this idea are recent observations of excess infrared radiation and X-ray emissions from the center, hints that something hot and compact might be hiding in the dust, possibly a pulsar spinning invisibly behind its own birth cloud. Then there's the wild card. What if the remnant isn't where we think it should be? Some models propose the newborn neutron star received such a powerful kick from asymmetric neutrinos during the explosion that it was launched sideways at over 500 kilometers per second, fast enough to have already escaped the main debris field. Others entertain an even more radical possibility that the core collapsed directly into a black hole so small and quiet that it's currently undetectable. Both scenarios would rewrite our understanding of how compact objects form, especially since SN 1987A's progenitor was right on the borderline between stars destined to become neutron stars and those fated for black holes. Adding to the intrigue are the supernova's light echoes, ghostly reflections of the original explosion bouncing off interstellar dust clouds light years away. These delayed flashes act like cosmic time machines, letting astronomers study the event from multiple angles long after the fact. Some echoes show spectral signatures suggesting the explosion ejected clumps of radioactive nickel, a key element in supernova furnaces, in uneven patches, further evidence that the blast was anything but symmetrical. Perhaps the most thrilling development came in 2020, when the Atacama Large Millimeter Array spotted a hot, dense blob near the supernova's center emitting bizarre molecular emissions. Some researchers think this could be the first glimpse of the long-sought neutron star's influence, its fierce winds finally punching through the surrounding debris. Others caution it might just be another knot of shocked gas. Either way, SN 1987 refuses to fade into obscurity. Every new observation peels back another layer, proving that even the most studied cosmic events can still surprise us. This isn't just about one supernova, it's about rewriting the textbook on stellar deaths, because if a landmark explosion like this can defy expectations so spectacularly, what else have we gotten wrong about how stars live and die? The Large Magellanic Cloud's greatest gift might be the humility it forces upon us, reminding humanity that the universe always has another card up its sleeve. The Large Magellanic Cloud doesn't just flout expectations with its oddball stars and explosive phenomena, it bends the rules of galactic architecture itself. Unlike the neat, flat disks of most spiral galaxies, the LMC's disk twists and warps like a cosmic banana peel. Its outermost stars and gas clouds pulled upward on one side and downward on the other in a gravitational roller coaster. This isn't just a visual quirk, it's a glaring sign that the LMC has been through the celestial ringer. its structure stretched and distorted by violent encounters we're only beginning to piece together. The leading suspect behind this cosmic contortion, a billion-year-long gravitational tug-of-war with the Milky Way and its smaller sibling, the Small Magellanic Cloud. Every time these galaxies swing past each other, their gravity acts like an invisible hand, kneading the LMC's disk like dough. Recent simulations suggest the most dramatic warping likely occurred during a close encounter with the SMC around 1.5 billion years ago, a galactic sideswipe that sent shockwaves through the LMC's gas-rich disk, leaving it permanently kinked. But the Milky Way isn't innocent either. Our galaxy's immense gravity exerts a steady pull, twisting the LMC's outer regions over eons like a slow-motion game of tug-of-war. What's fascinating isn't just the warp itself, but how the galaxy responds to it. Most warped disks struggle to form stars efficiently. Their gas gets too stretched out or turbulent. Yet the LMC's twisted disk is an exception, brimming with active stellar nurseries. This defiance might come down to its unusually high gas content. While spiral galaxies like ours have mostly converted their gas into stars, the LMC remains a gas-rich holdout, its reservoirs of hydrogen so dense they can withstand the gravitational turmoil. Where other galaxies might see star formation snuffed out by distortions, the LMC's warp actually seems to fuel it. The bent disk funnels gas into overlapping streams, creating pressure waves that trigger new star birth even in the most distorted regions. Then there's the warp's eerie asymmetry. The northern half of the disk curls upward toward the Milky Way, while the southern half arcs downward, almost as if the galaxy is caught mid-flinch. Some researchers think this could betray the direction of past collisions, like a cosmic bruise revealing where the blows landed. Others point to the LMC's high dark matter content or lack thereof, as we've seen earlier, as a possible culprit, with unevenly distributed invisible mass tugging the disk into these odd angles. But the real surprise lies in the warp's longevity. Most galactic distortions fade over time as gravity smooths things out, yet the LMC's warp persists with stubborn clarity. This could mean the galaxy is still recovering from its last close encounter, or that new gravitational disturbances like unseen dark matter subhalos are actively reshaping it. Either way, the warp isn't just a fossil of past violence, it's a living, breathing feature still evolving as the LMC dances through space. For astronomers, this bent disk is more than a curiosity. It's a test case for how galaxies evolve under extreme conditions. By studying how gas moves through these twisted lanes, how star formation adapts, and how the warp interacts with surrounding structures like the Magellanic Stream, we're piecing together a playbook for galactic survival. Because if there's one lesson the LMC teaches us, it's that chaos isn't always destructive. Sometimes it's just another way to shine. Deep in the cosmic shadows of the Large Magellanic Cloud, an invisible phantom flickers in and out of existence, his 3, an X-ray source so elusive that astronomers debate whether it's even real. One moment, it blazes with the telltale glow of a black hole or neutron star devouring its companion. The next, it vanishes without a trace, leaving telescopes staring at empty space. This isn't just a cosmic glitch, it's a full-blown celestial hide-and-seek champion, and its game of peek-a-boo is rewriting what we thought we knew about how these violent binaries behave. What makes his 3 so baffling isn't just its intermittency, it's the sheer extremes of its behavior. When active, its X-ray output rivals some of the brightest high-energy sources in the LMC, suggesting a compact object like a black hole gorging on stolen stellar material. But unlike steady X-ray binaries that hum along predictably, his 3 switches off so completely that it defies detection for months or even years. Some observations suggest its brightness can drop by a factor of 1,000 between outbursts, as if a cosmic dimmer switch gets flicked at random. The leading theory points to an eccentric orbit, a neutron star or black hole locked in a lopsided dance with a companion star, only flaring up when it swings close enough to siphon gas during periodic close encounters. Imagine a lighthouse whose beam only becomes visible when it aligns with a narrow slit in a rotating wall, but even this explanation falls short. His 3's outbursts don't follow any discernible timetable, leaving astronomers to wonder if something far stranger is at play, like a warped accretion disk that periodically clogs and unclogs, or a companion star with erratic stellar winds that sometimes choke off the flow of fuel entirely. Then there's the mystery of its invisibility between flares. Most transient X-ray sources leave behind faint echoes, heated gas, glowing debris, but his 3 goes radio silent so thoroughly that some researchers speculate it might not even be a single object. Could we be seeing multiple unrelated X-ray events along the same line of sight, masquerading as one intermittent source? Or is this the signature of an entirely new class of object, one that switches between states we've never before documented? The stakes are higher than they seem. If his 3 is a black hole, its stealthy nature suggests we've been underestimating how many of these dark predators might be lurking unseen in galaxies. If it's a neutron star, its extreme variability could hint at magnetic field behaviors we've never witnessed. Every flicker is a coded message, offering clues about the most violent relationships in the universe. And the Large Magellanic Cloud, as always, is the perfect stage for this cosmic mystery play. Deep in the stellar census of the Large Magellanic Cloud, astronomers have stumbled upon a glaring cosmic discrepancy. Where there should be crowds of aging red supergiants, the galaxy shows only scattered stragglers. This red supergiant problem isn't just a bookkeeping error. It's a direct challenge to our understanding of how massive stars spend their final years. These swollen, cooling stars, the evolutionary endpoint for suns between 8 and 40 times the mass of our own, should be abundant in a galaxy like the LMC, where star formation has been vigorous for eons. Yet surveys consistently find fewer than half the predicted number, as if some unseen force is prematurely snuffing them out. The heart of the mystery lies in mass loss, the process by which stars shed their outer layers as they age. Red supergiants are famously leaky, gusting away solar winds so dense they can lose an entire sun's worth of material in just 1 million years. But current models suggest this gradual shedding should still leave plenty of time for these stars to linger visibly before collapsing into supernova. The LMC's shortage implies something is accelerating their demise, stripping them down to their cores faster than theory allows. Some researchers point to enhanced mass loss rates in low metallicity environments like the LMC, where the scarcity of heavy elements makes stellar winds more efficient at carrying away material. Others speculate that hidden instabilities, perhaps violent pulsations or undiscovered magnetic mechanisms, might be tearing these giants apart from within. Complicating matters is the role of binaries. Many massive stars don't evolve in isolation. They're locked in gravitational dances with companions that can steal their outer layers or trigger premature eruptions. If a significant fraction of potential red supergiants are being stripped by unseen partners, that could explain their apparent absence. They're skipping the red supergiant phase entirely, transitioning directly from blue supergiants to Wolf-Rayet stars or exploding as stripped envelope supernova. The LMC's metallicity might amplify this effect, as lower metal content reduces opacity in stellar winds, making mass transfer between binary partners even more efficient. Then there's the supernova connection. If red supergiants are vanishing prematurely, that should alter the types of stellar explosions we observe. Type IIP supernova, the classic plateau supernova produced by red supergiant explosions, are indeed rarer in the LMC than expected, while more exotic subtypes like type IB or IB, which come from partially stripped stars, appear overrepresented. It's as if the galaxy's stellar population is cheating death, skipping the red supergiant stage and jumping straight to explosive endings. This isn't just academic curiosity. Red supergiants are cosmic alchemists, forging and dispersing heavy elements that seed future generations of stars and planets. If they're cutting their lives short, that changes the chemical enrichment timeline of entire galaxies. The LMC's anomalous population might hold the key to understanding why galaxies age the way they do, and whether our models of cosmic evolution need a fundamental rewrite. Every missing red supergiant is a silent witness to processes we're only beginning to glimpse, hidden in the turbulent winds of dying stars. Among the swirling currents of gas that make up the Large Magellanic Cloud, something extraordinary lurks, entire rivers of molecular clouds moving against the galaxy's spin, like salmon swimming upstream. These counter-rotating gas clouds aren't just curiosities, they're cosmic contradictions, challenging everything we thought we knew about how galaxies organize themselves. Normally, all the material in a galactic disk moves in concert, orbiting in the same direction like a well-choreographed dance. But here, vast clouds of hydrogen and dust barrel backward, defying the flow as if they've arrived from some alien corner of the universe. The leading explanation for these rogue clouds points to a dramatic theft in progress. The LMC, locked in a gravitational tug-of-war with the Milky Way and the small Magellanic Cloud, might be siphoning gas from its neighbors, or even snatching strays from the sparse intergalactic medium. Picture a galaxy-sized net cast into the cosmic void, hauling in stray gas clouds that, once captured, retain their original momentum, spinning opposite to the LMC's native material. Supporting this idea are observations of the Magellanic Stream, that immense ribbon of gas torn from both Magellanic Clouds, which shows hints of chaotic motion and infalling debris. But there's a wilder possibility. These backward spinning clouds could be the scars of an ancient galactic merger. Billions of years ago, the LMC might have collided with and consumed a smaller dwarf galaxy, one that approached from the opposite direction, imprinting its retrograde motion onto the gas it left behind. We see hints of this in other galaxies, where mergers leave behind counter-rotating stars and gas as celestial fingerprints. If true, the LMC's rebellious clouds might be the ghostly remnants of a long-vanished sibling, its final protest against being swallowed whole. What's fascinating isn't just their existence, but their survival. Gas clouds moving against the flow should collide with their forward-orbiting counterparts, dissipating their energy and eventually falling in line. Yet these clouds persist, their structure remarkably intact. Some researchers suspect magnetic fields might be shielding them, acting like invisible armor that keeps them coherent despite the chaos. Others propose the LMC's turbulent environment, where supernova and stellar winds constantly stir the gas, might actually prolong their defiance, preventing them from fully blending in. Then there's the impact on star formation. Counter-rotating gas introduces turbulence, and turbulence breeds complexity. When these opposing flows collide, they create shock waves that compress gas into dense knots, sparking bursts of star birth in unexpected places. This might explain some of the LMC's oddly distributed stellar clusters, islands of young stars far from the galaxy's main star-forming regions, as if seeded by these chaotic interactions. The deeper we look, the more these backward clouds feel like cosmic insurgents, quietly reshaping the galaxy from within. They're a reminder that even in the vast, orderly dance of the cosmos, there's always room for rebellion, and sometimes it's the rebels that write the most interesting chapters in a galaxy's history. Globular clusters are supposed to be predictable, dense spheres of ancient stars orbiting galaxies like well-behaved cosmic suburbs. But nestled in the Large Magellanic Cloud, NGC 1846 breaks every expectation. At first glance, it looks like any other globular, a shimmering ball of stars over 1 billion years old. Peer closer, though, and something unsettling emerges. A shadowy void at its heart, a region where stars thin out dramatically, as if something unseen has been clearing the neighborhood. This isn't just an empty patch, it's a gravitational crime scene, and the prime suspect is either a lurking black hole or a phenomenon so strange, it challenges how we think star clusters evolve. The case for a black hole is compelling. Most globular clusters host intermediate mass black holes, celestial heavyweights with thousands of times the Sun's mass, but NGC 1846's dark core doesn't match the usual signs. There's no telltale X-ray glow from infalling gas, no frenzied stars whipping around an invisible monster. Instead, the stars near the center move with eerie uniformity, their orbits subtly distorted, as if tugged by something massive yet oddly placid. Some astronomers argue this could be the quietest black hole ever observed, one that's already devoured nearby stars and now lies dormant, its appetite temporarily sated. Others propose an even stranger idea. Maybe it's not a black hole at all, but a dense knot of stellar corpses, white dwarfs, neutron stars, and smaller black holes, sunk to the core through a process called dynamic friction. Here's how that would work. Over billions of years, heavier objects in a star cluster gradually lose energy to lighter ones, sinking toward the center like stones in molasses. If enough dead stars pile up, their collective gravity could mimic a single massive black hole, sculpting the same hollowed-out core without any one object dominating. The LMC's low metallicity makes this scenario plausible. Its stars leave behind more compact remnants than in metal-rich environments, creating perfect conditions for this cosmic sleight of hand. But the plot thickens when we compare NGC 1846 to other clusters. Most with similar stellar densities show obvious central black holes or at least chaotic stellar motions. This one's calm center is an outlier, raising questions about whether we're seeing a new class of globular one where dark matter, not just dead stars, might play a role. Some models suggest faint, ancient dark matter clumps could anchor these clusters, explaining their stability without invoking black holes. It's a radical idea, since globulars are thought to be largely devoid of dark matter. Yet if true, NGC 1846 could rewrite how these clusters form and survive. The answer might lie in the cluster's unique history. The LMC's turbulent environment, full of galactic collisions and tidal shocks, could have stripped away NGC 1846's outer stars, leaving its core oddly exposed. Or perhaps it's a cannibal, the remains of two smaller clusters merged together, their dark secrets amplified in the aftermath. Every observation adds layers to the puzzle, reminding us that even the oldest structures in the universe still hold surprises. What makes this dark core so captivating isn't just the mystery of what's hiding there, it's what that answer could reveal about the invisible scaffolding of the cosmos. Whether it's a black hole, a graveyard of stars, or something even stranger, NGC 1846 proves that sometimes the most profound truths lurk in the shadows. And in the Large Magellanic Cloud, where the rules of astrophysics seem made to be broken, this enigmatic cluster is just another piece of the puzzle waiting to be solved. Among the many ghosts of dead stars haunting the Large Magellanic Cloud, two planetary nebulae stand out not for their beauty, but for their frankly bizarre chemistry. SMP LMC 11 and 34 look like siblings at first glance, their glowing shells of gas expanding outward from white dwarf cores. Yet their spectral fingerprints tell a different story, one that reads like a mad scientist's experiment in stellar alchemy. These nebulae shouldn't exist as they do, with chemical compositions that defy the standard playbook of dying stars, forcing astronomers to rethink how sun-like stars enrich the cosmos in their final breaths. Take SMP LMC 34 first. Its outer shell blazes with oxygen, neon, and argon, the expected remnants of nuclear fusion in a star's late life convulsions. But peer deeper, and the inner regions reveal an unsettling surprise: carbon-rich compounds alongside silicate dust, a combination so contradictory it's like finding ice and fire coexisting in perfect balance. This dual chemistry is the celestial equivalent of oil and water mixing, theoretically impossible under normal conditions. Oxygen-rich and carbon-rich zones repel each other chemically. One should dominate and erase the other. Yet here they are, layered like some cosmic onion, preserved in defiance of thermodynamic laws. SMP-LMC 11 doubles down on the mystery. While most planetary nebulae show smooth chemical gradients, this one's elements are clumped in chaotic pockets, knots of nitrogen jammed against helium-rich regions, with bizarre spikes of sulfur stitching through both. It's as if the dying star didn't just gently expel its outer layers, but coughed them up in fitful, uneven heaves. The leading theory, a violent dance with a binary companion star, might have stirred the stellar pot during the nebula's formation, churning the star's innards like a blender before ejection. Infrared observations back this up, showing lopsided gas distributions that hint at gravitational tugs from an unseen partner. What rattles scientists most isn't just the odd compositions, it's the implications for nucleosynthesis, the cosmic process that forges elements inside stars. These nebulae suggest low to medium mass stars, long thought to be predictable in their chemical outputs, might have wildcards up their sleeves. Maybe dredge-up events where convection drags deep material to the surface operate differently in the LMC's low-metal environment. Or perhaps magnetic fields, stronger in certain stellar lineages, twist fusion products into unnatural arrangements before expulsion. The stakes go beyond two strange nebulas. These objects are time capsules, locking in snapshots of how stars recycle their guts into the galactic ecosystem. If standard models can't explain SMP-LMC 11 and 34's chemistry, that means we're missing pieces in our understanding of how galaxies, including our own, get seeded with the building blocks of planets and life. Every anomalous spectral line is a clue whispering secrets about the chaotic, messy, and utterly unpredictable ways stars choose to die. And in the Large Magellanic Cloud, where cosmic rules seem optional, these twin enigmas are just another reminder. The universe loves a good plot twist. Most star clusters live out their lives in quiet orbits, content to circle their parent galaxy's core like well-behaved cosmic suburbs. But NGC 2157 isn't most clusters. This young, blazing congregation of stars, barely 30 million years old, has decided to go rogue, drifting away from its birthplace at speeds that leave astronomers scratching their heads. Located in the Large Magellanic Cloud's outer reaches, this runaway cluster is streaking through space with enough momentum to escape the galaxy's gravitational grip entirely, which raises a glaring question. What kind of cosmic slingshot could fling millions of stars into exile? The prime suspect is a gravitational kick, a violent encounter with something massive enough to send the cluster careening. Picture this: NGC 2157 once orbited near the LMC's bustling central regions where dense star clusters jostle for space. During one close pass with a particularly hefty neighbor, the gravitational tug of war might have acted like a cosmic catapult, flinging NGC 2157 outward while stealing some of its stars in the process. Supporting this idea are observations of the cluster's asymmetrical shape. Its outer edges appear stretched, as if part of it got left behind in the chaos. But there's another possibility: tidal forces. The LMC isn't just floating peacefully, it's locked in a slow motion dance with the Milky Way, and every close pass sends tidal shockwaves rippling through its gas and stars. If NGC 2157 found itself caught in one of these gravitational tsunamis, the sudden stretch and pull could have given it the boost it needed to break free. Unlike the sudden kick theory, this scenario would explain the cluster's unusually high velocity without requiring a single catastrophic event. Instead, it's the cumulative effect of the galaxy's turbulent environment, like a boat pushed steadily by waves until it drifts out to sea. What's fascinating isn't just how NGC 2157 got ejected, but what it's leaving behind. Most runaway stars are solitary lone wolves cast adrift by supernova kicks or binary breakups. But an entire cluster, that's rare. Its survival suggests an impressive internal cohesion, with the stars' mutual gravity holding them together even as external forces try to tear them apart. If the cluster can stay intact, it might eventually become a globular cluster in its own right, an ancient relic of its youthful escape drifting forever between galaxies. Yet the biggest mystery isn't its past, it's its future. Without the protective cocoon of the LMC's gas-rich disk, NGC 2157 is exposed to the harsh tides of intergalactic space. Over billions of years, those forces could strip it apart, scattering its stars into the void. Or, if it's dense enough, it might endure as a fossil of its former self, a ghostly reminder that even in the cosmos, some things refuse to stay where they're put. In the end, NGC 2157 isn't just running away, it's writing its own rules. The Milky Way has its famous Fermi bubbles towering gamma-ray, emitting structures ballooning from our galaxy's core. But look toward the Large Magellanic Cloud, and you'll find something eerily similar. Faint, ghostly lobes of high-energy radiation stretching thousands of light-years above and below its disk. These aren't just cosmic echoes, they're a puzzle wrapped in gamma rays, hinting at violent events buried deep in the LMC's past. What could have unleashed enough energy to sculpt these colossal structures in a galaxy a fraction of our Milky Way size? The Fermi bubbles in our own galaxy are thought to be relics of an ancient outburst from Sagittarius A, the supermassive black hole at the Milky Way's heart. But here's the twist: the LMC doesn't have a central supermassive black hole. Its gamma-ray lobes must have a different origin, and astronomers are chasing two leading suspects. The first, a frenzy of star formation so intense it generated galaxy-scale winds. Picture millions of supernova and stellar winds conspiring to blow a bubble of hot gas out of the disk, accelerating particles to near light speed along the way. The Tarantula Nebula, the LMC's most prolific stellar nursery, could have been ground zero, its non-stop star birth pumping energy into the galaxy's halo like a cosmic bellows. The second possibility is even more intriguing. What if the LMC once hosted a rogue active galactic nucleus, a temporary black hole powerhouse now gone dormant? While the LMC lacks a permanent supermassive black hole, it's possible a smaller, wandering black hole briefly went haywire, gorging on gas and unleashing jets powerful enough to mimic AGN activity. We've seen such mini-AGN behavior in other dwarf galaxies, where intermediate mass black holes flare up unexpectedly. If this happened in the LMC, even briefly, it could have inflated these gamma-ray structures before fading into obscurity. What's striking is how different the LMC's bubbles look compared to the Milky Way's. Ours are symmetrical, towering twins, while the LMC's are lopsided and fragmented like a half-deflated balloon. This asymmetry might be a clue. Perhaps the LMC's turbulent history of galactic collisions and tidal forces twisted the bubbles out of shape. Or maybe they're younger, still in the process of forming, their structure not yet smoothed by time. Then there's the puzzle of their faintness. Gamma-ray bubbles should shine brightly with the energy of their creation, yet the LMC's are barely detectable. One explanation points to the galaxy's low metallicity. With fewer heavy elements to act as cosmic accelerators, particles might not reach the energies needed for a stronger glow. Alternatively, the bubbles could be far older than we think, their radiation dimmed by eons of expansion into the void. The implications ripple beyond the LMC. If starburst winds alone can create Fermi-like structures, that reshapes how we interpret similar features in distant galaxies. And if a dwarf galaxy like the LMC can mimic AGN behavior even briefly, it forces us to reconsider what triggers these universal outbursts. Every flicker of gamma rays from these ghostly lobes is a message, a reminder that even the smallest galaxies can unleash cosmic tempests, and their echoes linger long after the storm has passed. Most stars that go supernova don't get a second act. They either collapse into black holes or leave behind neutron stars as their final tombstones. But deep in the Large Magellanic Cloud, nestled within the tangled wreckage of supernova remnant DML-241, there's a star that refused to follow the script. Meet the zombie star, a massive stellar survivor that somehow endured its partner's catastrophic explosion and lived to tell the tale. This isn't just a cosmic oddity, it's a celestial defiance of physics as we know it, forcing astronomers to rethink how binary systems weather the most violent events in the universe. The story begins with an unequal partnership. Before the explosion, DML-241 was a binary system, a massive star paired with an even larger companion. When the more massive star exhausted its fuel, it collapsed under its own gravity and detonated as a supernova, blasting its outer layers into space in a fireball visible across the galaxy. Conventional wisdom says the companion star should have been either obliterated by the blast or sent careening into space like a celestial cue ball, but this one. It's still here, orbiting the supernova's aftermath as if nothing happened. What makes this survivor so baffling is the sheer force it withstood. Supernova release enough energy in seconds to outshine entire galaxies, with shockwaves that can rip nearby stars apart. Yet observations from Chandra and Hubble reveal the zombie star not only survived, it's practically unscathed. Its outer atmosphere shows signs of being scorched by the blast, like a tree charred but still standing after a wildfire, but its core remains intact, still burning steadily. This isn't just luck, it's a cosmic anomaly that challenges our models of stellar endurance. The key might lie in the star's unusual orbit. Most binary systems have tight, circular paths, leaving the companion star vulnerable when its partner explodes. But DML-241's survivor was likely in a wide, elliptical orbit, putting it at a safer distance when the supernova erupted. Combine that with the star's own dense stellar wind, a protective bubble of charged particles, and it may have had just enough shielding to weather the storm. Still, even with these advantages, the fact that it held onto its place in the system is nothing short of miraculous. Now here's where it gets even weirder. The zombie star isn't just sitting quietly in the wreckage, it's interacting with it. X-ray observations show its stellar wind colliding with the supernova remnants' expanding shockwave, creating a glowing boundary where two epochs of stellar violence meet. This collision is generating temperatures in the millions of degrees, lighting up the surrounding gas like a neon sign in the cosmic dark. It's a living laboratory for studying how stars and supernova debris coexist, offering clues about how elements forged in the explosion get recycled into future generations of stars and planets. But the biggest question isn't how this star survived, it's what happens next. The zombie star is destined to explode too one day. When it does, will its partner, now a neutron star or black hole, endure the same way? Or will the second supernova finally tear this stubborn system apart? Every observation peels back another layer of the mystery, reminding us that even in death, stars can defy expectations. And in the Large Magellanic Cloud, where cosmic rules seem more like suggestions, the zombie star stands as a testament to the universe's endless capacity to surprise. Among the many pulsating stars in the Large Magellanic Cloud, a select few march to the slowest, most deliberate beat in the cosmos, ultra-long period variables, stellar giants whose brightness fluctuates not over days or months but across decades. These aren't your typical variable stars, they're cosmic metronomes ticking at a glacial pace, their rhythms so prolonged they defy conventional explanations. Imagine a star so vast its surface takes years to rise and fall like a slow-motion heartbeat, or a binary system so deeply entwined that one star's death throws stretch across human lifetimes. The LMC hosts some of the most extreme examples of these enigmatic objects, and their bizarre behavior might rewrite what we know about stellar evolution's outer limits. The defining trait of these stars is their absurdly long cycles. Some take anywhere from 10 to 50 years to complete a single pulsation. Most variable stars, like Cepheids or Mera variables, operate on timescales we can observe within a single research grant. But ultra-long period variables demand patience, their full cycles often spanning an astronomer's entire career. The record holder, a red supergiant in the LMC catalogued as HV 2430, whose dimming and brightening unfolds over 45 years. That's longer than the gap between the first moon landing and the launch of the Webb telescope. What fuels these marathon pulsations? One leading theory points to stars teetering on the edge of instability, red supergiants so bloated their outer layers hang by a gravitational thread. In these behemoths, convection becomes sluggish, with heat bubbling to the surface at a crawl. Like a pot of syrup left to simmer, these stars don't boil over quickly, they oscillate in slow, ponderous waves. But there's a catch. Models suggest even the largest red supergiants shouldn't pulsate this slowly unless something else is at play. That's where the exotic explanations kick in. Enter Thorne-Zitkow objects, theoretical hybrid stars so bizarre they sound like science fiction. Picture a red supergiant with a neutron star nestled at its core, the remnant of a swallowed companion. The neutron star's immense gravity would stir the supergiant's interior like a spoon in molasses, creating peculiar oscillations that could manifest as ultra-long period variability. While no confirmed Thorne-Zitkow objects exist yet, the LMC's slow pulsators are prime candidates. Their chemical signatures, enhanced lithium and heavy elements, could betray the presence of a neutron core silently altering their evolution. Then there's the binary interaction angle. Some ultra-long period variables might actually be two stars in a slow, decaying dance, where one star's outer layers are gradually stripped away by its partner. As material spirals between them, it forms a vast, distended envelope that pulsates erratically over decades. The LMC's low metallicity makes these interactions even messier. With fewer heavy elements to radiate away heat, the stolen gas could linger longer, amplifying the variability. The implications stretch far beyond stellar curiosities. If Thorne-Zitkow objects are real, they represent an entirely unseen phase of stellar evolution. And if binary interactions are driving these slow-motion pulsations, they could explain oddities like missing supernova progenitors, stars that vanish without the expected explosion. Every flicker of these cosmic slowpokes is a data point in a decades-long experiment, one that challenges us to rethink how stars live, die, and defy expectations. In the LMC, where cosmic norms go to unravel, these ultra-long period variables are the ultimate test of patience and the ultimate reward for those willing to watch the clock. Deep in the Large Magellanic Cloud, a cosmic fugitive spins in isolation SGR 0526-66, a magnetar with no past, no visible origin, and no explanation for how it wound up so utterly alone. This ultra-dense, hypermagnetic neutron star should be sitting at the heart of a supernova remnant, surrounded by the glowing wreckage of the explosion that birthed it. Instead, it drifts through empty space like a bullet fired from a gun no one can find, its presence defying everything we know about how these exotic stellar corpses come to be. Magnetars are already extreme neutron stars with magnetic fields so powerful they could strip the data off a credit card from halfway across the solar system. Most form when massive stars collapse in supernova, their cores compressing into whirling dynamos of unimaginable density. The explosions that create them typically leave behind expansive, glowing remnants that persist for tens of thousands of years. Yet SGR 0526-66 has no such home, no gaseous shell, no debris field, just the magnetar itself, spinning silently in the void as if it appeared out of nowhere. So where did its supernova go? One possibility is that this magnetar was violently ejected from its birthplace. In dense star clusters, the gravitational chaos of multiple massive stars can slingshot newborn neutron stars into space at incredible speeds. If SGR 0526-66 got such a kick, it might have raced away from its remnant fast enough to leave it far behind like a runner bolting from the starting line while the smoke of the gun lingers in place. Observations support this idea. The magnetar is moving swiftly through space, and its trajectory, when traced backward, points toward a region thick with young stars that could have hosted its explosive birth. But there's a catch. Even if it was ejected, the remnant should still be visible. Supernova debris sticks around for millennia, and nothing in the LMC's known history suggests a mechanism that could make one vanish prematurely. That's led to a wilder theory. Maybe the original explosion was fundamentally different, a failed supernova that produced a magnetar without the usual fanfare. Some models suggest stars rich in heavy elements might collapse directly into magnetars with fainter, shorter-lived remnants, their outer layers falling back onto the core instead of exploding outward. If true, SGR 0526-66 could be the prototype for a whole new class of stellar deaths. Then there's the timing problem. Magnetars are thought to lose their extreme magnetic fields within about 10,000 years, fading into more typical neutron stars. If this one's original remnant dissipated, it must have happened at breakneck speed by cosmic standards. That raises eyebrow-raising questions. Could some supernova remnants vanish faster in the LMC's low metallicity environment? Or did this magnetar form through a freak event like the merger of two white dwarfs, bypassing the traditional supernova pathway altogether? For now, SGR 0526-66 keeps its secrets. Every pulse of its X-ray emissions is a clue, a whisper from an object that refuses to fit neatly into our models. Whether it's a rebel ejected from its home or the product of a stellar death we don't yet understand, one thing is clear: the universe has more ways to make magnetars than we ever imagined. And in the Large Magellanic Cloud, where cosmic rules are more like suggestions, this orphaned oddity is proof that even the most violent stellar endings can leave behind mysteries that outlast the explosions themselves. Stretching across the Large Magellanic Cloud like a celestial necklace, the string of pearls presents one of the most striking cosmic contradictions, a perfectly aligned sequence of glowing star-forming regions, each blazing with newborn stars strung together in an unnatural straight line. These aren't randomly scattered stellar nurseries, they're precision-placed with near-perfect spacing, as if some cosmic hand threaded them together. The pearls themselves are HI regions, vast clouds of ionized hydrogen lit up by the ultraviolet fury of massive young stars, but their formation story is anything but ordinary. The conventional explanation points to a fragment of a spiral arm. In most galaxies, star-forming regions trace graceful, curving arcs along these structures, following the gravitational contours of rotating gas. But the LMC's turbulent history might have torn one of these arms apart, leaving behind this linear remnant, like a single pearl strand snapped from a larger collar. Supporting this idea is the fact that the string aligns roughly with the galaxy's overall rotation, hinting it could be the last intact piece of a structure otherwise shredded by gravitational encounters. Yet there's a competing theory that's far more dramatic. Some astronomers argue this isn't a spiral arm at all, but a fossilized shockwave, a cosmic tsunami frozen in time. Picture a titanic collision between gas clouds or a chain reaction of supernova explosions millions of years ago. The resulting pressure wave would have rippled through the interstellar medium, compressing gas into dense pockets that later collapsed into stars. The string's precise linearity and uniform spacing would then be the imprint of that ancient wave, like footprints left in wet sand after the tide recedes. The evidence for this explosive origin is compelling. Several of the pearls show signs of synchronized stellar ages, their stars formed around the same epoch, suggesting a single triggering event. Even more telling is the presence of high-velocity gas flows around the string, streaming away perpendicular to the line as if pushed outward by the same force that created it. It's as if we're seeing the aftermath of a stellar domino effect, where one massive star's death kicked off a chain reaction of birth along a perfect vector. But the mystery doesn't end there. The string of pearls challenges our assumptions about how galaxies organize their star formation. In the Milky Way, such linear arrangements are unheard of. Our star-forming regions follow the graceful curves of spiral arms without exception. The LMC's low metallicity, its scarcity of heavy elements, might hold the key. With fewer metals to help gas cool and fragment, shockwaves could propagate farther without dissipating, creating these bizarrely straight-line features. Alternatively, the galaxy's weaker gravity compared to spirals like ours might allow structures to remain coherent longer without warping into curves. Then there's the tantalizing possibility that we're witnessing a cosmic coincidence, a chance alignment of unrelated HII regions that only appear connected from our vantage point. But the odds of such perfection emerging randomly are astronomically low. The string's pearls aren't just visually aligned, their chemistry and kinematics are interlinked, betraying a shared origin, whether from a spiral arm fragment or a catastrophic shockwave. What makes this structure so captivating isn't just its beauty, it's the window it provides into the LMC's chaotic soul. A galaxy without clear spiral arms, yet capable of sculpting something so geometrically pristine, defies easy categorization. Whether it's the ghost of a disrupted arm or the echo of a forgotten explosion, the string of pearls reminds us that even in the messiest corners of the universe, patterns emerge, and sometimes, against all odds, they line up perfectly. Among the ancient stellar crowds of the Large Magellanic Cloud's globular clusters, strange outliers blaze with rebellious youth, blue stragglers, stars that shine hotter and brighter than their neighbors, defying the natural aging process. These celestial Benjamin buttons shouldn't exist in clusters where every other star has long since cooled into red old age, yet here they are, pockets of blue defiance scattered across the LMC in numbers that far exceed predictions. Their very presence suggests cosmic cheating, either through stellar vampirism or violent collisions, and the LMC's unique environment seems to be stacking the deck in their favor. The mystery begins with stellar timelines. In any given star cluster, all members typically form around the same epoch from the same gas cloud, meaning their evolutionary path should sync up. After billions of years, most stars in these clusters have exhausted their hydrogen fuel and expanded into red giants or faded into dwarfs. Blue stragglers break this rule, appearing as if they've hit the cosmic snooze button on aging. Their blue-white hue and high temperature indicate they're still burning hydrogen vigorously, behavior expected of stars 1/10 their true age. Two leading theories attempt to explain this anomaly, both involving cosmic shortcuts to extended youth. The first is binary mass transfer, a scenario where one star in a close pair siphons material from its companion like a stellar parasite. As the donor star gets stripped, the thief gains fresh hydrogen fuel, effectively resetting its internal clock while growing more massive and luminous. The LMC's dense clusters provide perfect breeding grounds for this vampirism, with stars packed so tightly that binary interactions are inevitable. But the second theory is even more dramatic: stellar collisions. In the crowded core of globular clusters, stars occasionally smash together in violent mergers. Imagine two aging stars, each halfway through their fuel supply, colliding and combining into a single, more massive star with a reshuffled core. This newborn hybrid would appear younger and bluer than its peers, despite technically being the same age. The LMC's low metallicity amplifies this effect. With fewer heavy elements to act as stellar lubricants, collisions result in more complete mergers rather than messy disruptions. What makes the LMC's blue straggler overdensity truly puzzling is the sheer scale. Some clusters host dozens of these objects, far more than expected even in dense environments. This suggests third factors might be at play, like hierarchical triple-star systems where complex gravitational dances periodically funnel material onto one lucky participant. Others speculate the LMC's turbulent history could have pre-processed these clusters, stirring them up during past galactic encounters to boost interaction rates. The implications ripple beyond mere curiosity. Blue stragglers are cosmic alchemists. Their unusual evolution produces distinct chemical signatures that get recycled into future stars. If collisions dominate their formation, they should leave behind more lithium and carbon anomalies than the mass transfer scenario. By studying their light with spectrographs, astronomers are essentially performing stellar autopsies, reconstructing the violent or vampiric events that birthed them. Yet the most tantalizing clue comes from their distribution. In the LMC, blue stragglers aren't randomly scattered. They cluster near the centers of their host globulars, gravitating toward the densest regions where interactions are most likely. Some even show evidence of rapid rotation, spinning like tops as if still dizzy from the mergers that created them. These patterns hint at an invisible hierarchy of formation mechanisms, with quieter binary theft happening in the outskirts while chaotic collisions reign in the urban cores. As telescopes probe deeper into these stellar anomalies, one thing becomes clear. The Large Magellanic Cloud isn't just hosting blue stragglers, it's mass-producing them. Whether through galactic conditions that favor close encounters or some unseen factor boosting collision rates, this dwarf galaxy has become a factory for stellar rebirths. And each one tells a story of survival, theft, or cosmic violence written in the light of stars that refuse to fade quietly into the night. Tucked away in the outskirts of the Large Magellanic Cloud lies a cosmic graveyard of sorts, a sprawling region littered with the remnants of a stellar frenzy so intense it once set the entire galaxy ablaze. This fossil starburst zone, now quiet and aging, tells the story of a bygone era when star formation erupted across the LMC on a scale that dwarfs anything seen today. The evidence is etched into the very fabric of this region. Dense clusters of ancient, massive stars that burned out long ago, their explosive death seeding the area with heavy elements, while the faint, glowing shells of long-dead supernova linger like ghostly echoes. What triggered this galactic firestorm? The clues point to gravitational chaos. Around 2 to 3 billion years ago, the LMC likely had a dramatic close encounter with its smaller sibling, the Small Magellanic Cloud. As the two galaxies swept past each other, their mutual gravitational pull sent shockwaves through their gas reservoirs, compressing vast clouds of hydrogen into dense knots that ignited a frenzy of star birth. Imagine two celestial titans brushing shoulders in the cosmic dark, their gravitational wake rippling through each other's structures like stones tossed into a pond. The LMC, already gas-rich, responded by lighting up like a firework, birthing stars at rates that would put modern star-forming regions like the Tarantula Nebula to shame. But the smoking gun isn't just the clusters themselves, it's their distribution. Unlike younger stars, which are scattered across the LMC's spiral-like patterns, these ancient starburst relics are oddly concentrated in a broad, asymmetrical band stretching through the galaxy's outer reaches. This isn't random, it's the signature of tidal forces in action. When galaxies interact, their gravitational dance doesn't just trigger star formation, it can slosh gas around like water in a moving bucket, piling it up in some areas while leaving others bare. The fossil starburst region's skewed layout matches simulations of such encounters, where gas was funneled into specific zones before collapsing into stars. Adding to the intrigue is the chemical fingerprint of these aging stars. Spectroscopic studies reveal unusually high abundances of elements like oxygen and neon, the telltale byproducts of short-lived massive stars that lived fast and died young. This fits perfectly with the starburst scenario. When star formation goes into overdrive, it produces an excess of these massive stars, which then explode as supernova, enriching the surrounding gas with their fused interiors. The fact that we see these elements concentrated in this region, like cosmic breadcrumbs, suggests it was once the epicenter of a galaxy-wide explosion of stellar life. Yet the story doesn't end there. The Milky Way may have played a role too. As the LMC orbits our galaxy, tidal forces from the Milky Way's gravity could have further stirred the pot, amplifying the starburst caused by the SMC encounter. It's a cosmic tag team effect, one galaxy's gravitational nudge setting the stage for another's disruption. This might explain why the fossil starburst isn't just a localized event but a galaxy-wide phenomenon, with traces of synchronized star birth cropping up even in the LMC's more secluded corners. Today, this region is a shadow of its former self, a quieter, older version of the stellar fireworks that once dominated, but its legacy lives on. The heavy elements forged in that ancient frenzy now drift through the LMC's interstellar medium, seeding future generations of stars and planets. And the clusters left behind, though fading, serve as a reminder that even the calmest-looking galaxies have violent pasts. The fossil starburst isn't just a relic, it's a testament to the LMC's dynamic history, written in the language of stars that flared brilliantly before vanishing into the cosmic dark. In the stellar retirement homes of the Large Magellanic Cloud, where aging stars puff up into bloated giants during their final acts, there's a glaring absence where there should be an entire population. These are carbon stars, crimson-hued giants that should be plentiful among the LMC's asymptotic giant branch AGB stars, yet they're conspicuously scarce. It's like walking into a theater expecting a full cast, only to find half the actors never showed up. Carbon stars form when AGB stars, sun-like stars in their death throes, fuse helium into carbon in their cores while dredging this material up to their surfaces through massive convection currents. Normally, this process enriches a star's outer layers with carbon until it outweighs the oxygen present, creating a sooty atmosphere that glows like a cosmic ember. These carbon-rich atmospheres are so distinct they can outshine entire galaxies in infrared light. Yet in the LMC, despite swarms of AGB stars, these carbon-rich variants are oddly rare. The root of this cosmic shortfall likely lies in the LMC's metallicity, its lower abundance of heavy elements compared to galaxies like our Milky Way. In metal-poor environments, stars form with less oxygen in their initial composition. That might sound trivial, but here's the catch. For a star to become a carbon star, the carbon it produces internally must exceed the oxygen left over from its birth. In the LMC's oxygen-poor stars, that balance is harder to achieve. Even as dredge-up brings carbon to the surface, there's often still just enough primordial oxygen to bind with it, forming carbon monoxide instead of free carbon soot. The result, a star that should be a carbon star remains an oxygen-rich giant instead, its potential sooty glow chemically stifled, but metallicity isn't the only suspect. The LMC stars might be losing mass too efficiently during their AGB phase. Imagine a star shedding its outer layers like a snake sloughing skin. If it does this too quickly, the carbon produced deep inside gets blown away before convection can bring enough to the surface to tip the scales. Some observations suggest the LMC's stellar winds are indeed more aggressive than in metal-rich galaxies, potentially stripping stars of their carbon potential before it can dominate their atmospheres. There's also the wild card of binary interactions. If an AGB star has a close companion, that partner could siphon away its carbon-enriched outer layers before they fully develop, like a thief stealing a painting before the final brushstrokes dry. Given the LMC's history of chaotic stellar encounters, this might explain why some would-be carbon stars never reach their full sooty glory. The implications ripple beyond stellar curiosities. Carbon stars are cosmic factories for dust, the very stuff that forms planets and shields young stellar nurseries from harsh radiation. Their scarcity in the LMC could mean the galaxy's interstellar environment is starved of certain types of dust grains, altering how future stars and planets form. It's a subtle difference, but in the grand tapestry of galactic evolution, even missing stars leave their mark. So while the LMC's carbon stars might be few, their absence speaks volumes, a silent testament to how chemistry, chaos, and the cosmos conspire to rewrite the rules of stellar retirement. And somewhere in that deficit, there's a lesson waiting to be uncovered about how galaxies forge the elements that build worlds. The Large Magellanic Cloud isn't just losing gas to the Milky Way's relentless gravity. It might be accidentally spawning new galaxies in the process. Drifting along the fringes of the LMC's distorted disk, a peculiar knot of stars and gas has astronomers buzzing with possibility. A potential tidal dwarf galaxy in the making, a celestial underdog struggling to survive against the very forces that created it. Tidal dwarfs are cosmic orphans, compact galaxies birthed not from primordial gas, but from the debris of galactic collisions or near misses. When galaxies graze each other, their gravitational tug of war can strip away vast ribbons of gas and stars, some of which may clump together under their own gravity, forming entirely new, albeit tiny, galactic entities. The LMC's candidate, still clinging to its tenuous identity amid the chaos, could be one such object, a fledgling system forged from the LMC's own cast-off material as it wrestles with the Milky Way's tides. What makes this candidate so compelling is its defiance. To qualify as a true tidal dwarf, it must meet two crucial criteria. It needs enough mass to hold itself together against the tidal forces trying to shred it, and it should harbor its own independent star formation, distinct from the LMC's main body. Preliminary observations reveal both. The cloud-like structure contains pockets of young, blue stars, evidence of recent starbirth, while its motion suggests it's not just drifting passively, but may have enough self-gravity to maintain cohesion. Yet survival is far from guaranteed. The Milky Way's tidal forces are relentless, and without a dark matter halo, something tidal dwarfs famously lack, this nascent galaxy is fighting gravity with one hand tied behind its back. Dark matter typically acts as cosmic glue, helping traditional galaxies resist disruption. But tidal dwarfs born from stripped gas inherit only the visible matter of their parent galaxies, leaving them shockingly vulnerable. Every close pass with the Milky Way or LMC stretches the candidate stars and gas like taffy, testing whether it can endure or will dissolve back into the intergalactic void. The stakes here aren't just about one struggling dwarf. If this object survives, it could reshape how we understand galaxy formation on the smallest scales. Tidal dwarfs are cosmic chimeras, hybrids that blur the line between galactic wreckage and bona fide galaxies. Their existence challenges the notion that all galaxies require dark matter to take shape, suggesting some might bootstrap themselves into existence through sheer density. The LMC's candidate, if confirmed, would join a rarefied club of such objects, offering a front-row seat to watch a galaxy being built or broken in real time. But there's a twist. This candidate might not be alone. Recent surveys hint at other gas-rich clumps along the LMC's distorted outskirts, each potentially the seed of a future tidal dwarf. It's as if the LMC, caught in the Milky Way's gravitational vise, is scattering cosmic breadcrumbs, some of which could sprout into something greater. Whether any endure long enough to earn the title of galaxy depends on a delicate balance of gravity, momentum, and chance. And in that uncertainty lies the fascination. The universe's smallest galaxies might not be born in the fiery collapse of primordial gas clouds, but in the quiet desperation of material fighting to survive against impossible odds. The star, now known as SN 2009 IP, spent years playing the ultimate cosmic prank, faking its own death not once but multiple times before finally taking its final bow with a genuine supernova. This supernova imposter first caught astronomers' attention in 2009 when it erupted with the brilliance of a stellar explosion, only to fade away and return to relative normality. Over the next 3 years, it staged repeated performances, flaring dramatically before settling down each time like an actor milking curtain calls. These outbursts weren't just minor hiccups. they released enough energy to outshine entire star clusters, mimicking the violence of true supernova while the star itself somehow clung to existence. What made SN 2009 IPS Theatrics so baffling was the sheer force of these false alarms. Most stars on the verge of collapse don't produce multiple precursor explosions. They build toward one cataclysmic finale. Yet this luminous blue variable, a massive and unstable type of star prone to extreme mood swings, seemed to be testing the limits of stellar endurance. Each eruption ejected vast amounts of material enough to form multiple planets while the star's core somehow remained intact. Spectroscopic analysis revealed shells of gas expanding outward in concentric layers like nested soap bubbles, each marking a previous near-death experience. The key to this erratic behavior might lie in the star's internal instability. As a massive, rapidly rotating star with intense stellar winds, SN 2009 IP was likely balancing on the knife's edge of self-destruction for decades. Every so often, pressures in its core would reach a breaking point, triggering violent pulsations that blasted away its outer layers without fully disrupting the core. Think of it like a pressure cooker intermittently releasing steam to avoid explosion, except in this case, each steam release was powerful enough to briefly outshine galaxies. Then came the final act. In 2012, SN 2009 IP appeared to erupt once more, but this time something was different. The light curve didn't fade as before. Instead, it plateaued, then surged again with even greater intensity. This was no imposter. The star had finally exhausted its ability to recover, its core collapsing in a genuine supernova. The spectacle was amplified by the star's previous outbursts. The ejected material from its fake explosions created a dense circumstellar environment, causing the supernova shockwave to plow through these pre-existing shells and generate extraordinary light displays. What fascinates astronomers isn't just the star's deceptive history, but what it reveals about the final moments of massive stars. SN 2009 IP suggests that some stellar deaths aren't sudden events, but drawn-out processes where the star wages an internal war against collapse, buying time through increasingly desperate eruptions. It's a reminder that even in the cosmos, not all endings come without warning. Some stars scream their intentions across the light years before taking their final bow. Among the many enigmas drifting through the Large Magellanic Cloud, there's a breed of cosmic shadows so elusive they're almost invisible, not for lack of light, but because they refuse to play by the usual rules of detection. These are the LMC's so-called dark gas clouds, vast reservoirs of molecular hydrogen lurking between the stars, detectable only through the faintest whispers of gamma rays while stubbornly avoiding the telltale signatures of carbon monoxide emission that typically betray such structures. It's as if the universe has hidden an entire population of gas clouds in plain sight, forcing astronomers to ask, what makes these shadows so different from the rest of the galaxy's interstellar medium? The mystery begins with the way we usually find gas clouds. In most galaxies, dense pockets of molecular hydrogen, the raw material for star formation, are traced through their carbon monoxide co-emissions. When starlight or cosmic rays energize these clouds, the CO molecules within them vibrate at specific frequencies, emitting radio waves that telescopes can easily pick up. But the LMC's dark gas clouds defy this expectation. Despite containing enough hydrogen to form thousands of stars, they show almost no CO emission at all, rendering them nearly invisible to traditional surveys. The only hint of their existence comes from gamma rays, high-energy photons produced when cosmic rays slam into the cloud's hydrogen nuclei. It's like finding a hidden room in a house by listening for echoes, even though the door is painted to blend into the wall. So what's shielding these clouds from view? One compelling theory points to their primordial origins. Unlike the gas in most galaxies, which has been cycled through generations of stars and enriched with heavy elements like carbon and oxygen, these dark clouds might be relics from an earlier cosmic era, pockets of nearly pristine hydrogen that avoided contamination by stellar winds and supernova. Without carbon, there's no CO to emit. Without metals to help the gas cool and clump, the hydrogen remains diffuse, resisting the gravitational collapse that would normally trigger star formation and illuminate these structures. In essence, these clouds could be cosmic time capsules, preserving conditions similar to those in the universe's infancy, before stars had peppered space with heavier elements. But there's a twist. The LMC's low metallicity might be amplifying this effect. Compared to the Milky Way, the LMC has fewer heavy elements overall, meaning even its normal gas clouds are already poorer in carbon and oxygen. In such an environment, the threshold for CO detection could be impossibly high, leaving vast swaths of hydrogen gas lurking just beneath our observational radar. Some simulations suggest that up to 30% of the LMC's molecular gas might exist in this shadowy form, enough to dramatically reshape our understanding of the galaxy's star-forming potential. The implications ripple far beyond the LMC. If dark gas clouds are this prevalent in a nearby dwarf galaxy, they might also exist in the distant metal-poor galaxies of the early universe, where heavy elements were even scarcer. That would mean we've been underestimating the reservoirs of raw material available for the first generations of stars, a realization that could rewrite models of cosmic dawn. Even more intriguing is the possibility that these clouds aren't just passive holdouts but active participants in galactic evolution. Without CO to radiate away heat, they might accumulate silently until gravitational instabilities or collisions with other gas streams finally trigger their collapse, leading to sudden, unexpected bursts of star formation. Yet the biggest question remains unanswered. How many more of these ghostly reservoirs are out there, and what role do they play in the life cycle of galaxies? Every gamma-ray flicker from the LMC's dark clouds is a clue, hinting at a hidden dimension of the interstellar medium, one where the universe's most basic ingredient lingers in the shadows, waiting for its moment to step into the light. Fast radio bursts, those fleeting, enigmatic blips of cosmic radiation, have puzzled astronomers since their discovery, lasting mere milliseconds yet packing the energy of hundreds of millions of suns. Their origins have been hotly debated. But in the Large Magellanic Cloud, we might finally have a smoking gun, a magnetar named SGR 1935 plus 2154, caught red-handed producing an FRB. This isn't just another detection, it's the first definitive link between these cosmic lightning strikes and the universe's most magnetic stellar corpses, and it's rewriting what we thought we knew about where and how FRBs form. The story begins with the magnetar's tantrum. In April 2020, this already unstable neutron star, known for its erratic X-ray flares, erupted with something new. A millisecond-long radio burst strikingly similar to the FRB spotted in distant galaxies. The timing was impeccable. Just as the magnetar's X-ray activity spiked, radio telescopes caught the telltale chirp of an FRB, its frequency drifting downward like a celestial slide whistle. For the first time, we had proof that magnetars, with their unimaginably strong magnetic fields, could produce these elusive signals. But here's where the LMC's environment twists the plot. Most FRBs detected elsewhere in the universe arrive dispersed, their signals stretched out as they traverse vast intergalactic distances, battling electrons along the way. The LMC's magnetar produced FRB, by contrast, showed remarkably little dispersion, a clue that it had traveled through relatively clean galactic surroundings. This makes sense. The LMC's low metallicity means fewer free electrons littering its interstellar medium, offering FRBs a clearer path than they'd find in metal-rich galaxies like our own. Compare this to the Milky Way's sole confirmed FRB, which originated from another magnetar, SGR 1935, plus 2154's galactic cousin, SGR 1935 plus 2154. That burst detected in 2020 was fainter and more scattered, its signal muddied by our galaxy's thicker interstellar soup. The difference highlights how a galaxy's chemical makeup, specifically its abundance of heavy elements, can shape the FRBs born within it. In metal-poor environments like the LMC, FRBs might emerge crisper and brighter, while in galaxies choked with stellar debris, they could arrive stretched and dimmed. The implications ripple beyond mere detection. If magnetars are indeed FRB factories, their prevalence in different galactic environments could explain why some galaxies seem to produce more bursts than others. The LMC, with its turbulent star-forming regions and history of stellar collisions, might be a magnetar nursery, cranking out these highly magnetic neutron stars at rates higher than more metal-rich galaxies. That could make dwarf galaxies like the LMC FRB hotspots, their chaotic births and low metallicity deaths creating perfect conditions for magnetar formation and the radio bursts they spawn. Yet mysteries remain. Why do only some magnetars produce FRBs while others stay radio silent? Is there a threshold of magnetic field strength or rotational energy required? And could some of the universe's more exotic FRBs, the ones that repeat unpredictably, be coming from magnetars in even more extreme environments? The LMC's magnetar offers a tantalizing starting point, but the story is far from complete. Every burst from this cosmic lighthouse is another piece of the puzzle, another clue in the quest to unravel one of the universe's most electrifying mysteries. Scattered across the Large Magellanic Cloud like pearls on a broken necklace, a strange arc of star clusters traces what might be the ghost of a galactic collision, or the echo of a resonance pattern frozen in time. This isn't a perfect ring, but a fragmented curve of stellar groupings, all roughly the same age and chemical composition, strung together in a formation too deliberate to be random. Astronomers call it the ring of clusters, though it's more of a ragged crescent, and its existence hints at violent gravitational encounters that reshaped the LMC's structure billions of years ago. The leading theory suggests this arc isn't just a chance alignment, it's a fossilized snapshot of a resonance, a gravitational ripple effect. Picture dropping a pebble into a pond. The ripples expand outward in perfect circles. Now imagine that pond is a galaxy, and the pebble is a close encounter with another galaxy. The LMC's ring of clusters may be the lingering imprint of such an event, where gravitational forces caused gas and stars to pile up along specific orbital paths, like cars slowing down at a traffic bottleneck. Over time, these crowded regions condensed into star clusters, leaving behind a skeletal outline of the original disturbance. But here's where it gets strange. The clusters in this arc aren't just spatially linked, they're cosmic twins, born around the same epoch from gas with matching chemical fingerprints. This synchronization suggests they formed from a single, galaxy-wide trigger, possibly during the LMC's last major interaction with the small Magellanic Cloud. As the two galaxies grazed each other, their mutual gravity could have sent shockwaves through the LMC's disk, compressing gas along a specific resonant orbit and igniting a burst of star formation that left these clusters as permanent mileposts. Yet there's a competing explanation, one that doesn't require a galactic collision. Some models propose the ring might be a standing density wave, a self-reinforcing pattern similar to the spiral arms in larger galaxies. In this scenario, the LMC's rotation creates natural zones where gas accumulates, not unlike how a record grooves vibrations at certain frequencies. These overdensities then birth star clusters at regular intervals, creating the illusion of a ring without any external trigger. The fact that the LMC lacks a strong central bar which typically anchors such structures makes this idea controversial, but not impossible. What's clear is that this structure isn't static. The clusters drift over time, tugged by the LMC's uneven gravity and interactions with the Milky Way. Some may eventually scatter, erasing the ring altogether, while others could be replenished by new clusters forming along the same resonant path. It's a celestial dance where the steps are written in gravity, and the music is the slow, relentless passage of time. This ghostly ring isn't just a curiosity, it's a key to decoding the LMC's turbulent past. By studying its geometry, astronomers can reconstruct the galaxy's dynamical history, like forensic scientists piecing together a crime scene. Every cluster in that arc is a witness, silently testifying to the forces that shaped one of the universe's most unpredictable galaxies. And as the LMC continues its slow-motion tango with the Milky Way, this fragile structure might yet reveal even deeper secrets about how galaxies evolve, and how even chaos can leave behind patterns etched in starlight. Amid the chaotic beauty of the Large Magellanic Cloud, one nebula stands out for its eerie symmetry, a cosmic hourglass of glowing gas that astronomers call a bipolar nebula. This striking structure bears an uncanny resemblance to one of the Milky Way's most enigmatic objects, the red rectangle. Both nebulae feature twin lobes of material erupting from a central star, their geometrically precise shapes resembling celestial stained glass. But look closer, and the differences between these distant cousins reveal how two galaxies can take the same stellar blueprint and produce wildly different results. The red rectangle, located about 2,300 light-years from Earth in our own galaxy, gets its name from its distinctive ruddy hue and angular structure. At its heart lies a dying star, a post-AGB binary system, whose intense ultraviolet radiation illuminates concentric rings of dust and gas ejected over millennia. What makes it truly bizarre is the near-perfect X shape formed by these rings, a pattern so precise it looks almost artificial. The secret lies in the central star's gravitational dance. Their orbital motion acts like a cosmic sprinkler, flinging material outward in opposing jets while shaping the surrounding nebula into this razor-edged form. Now shift your gaze to the LMC's bipolar nebula. At first glance, the structure appears similar twin cones of glowing gas stretching light years into space. But the devil's in the details. Unlike the red rectangle's tight, nested rings, the LMC's version is more chaotic, its lobes stubbier and less defined. This isn't an artist's meticulous etching, it's nature's rough sketch. The divergence starts with their central stars, while the red rectangle's binary system meticulously sculpts its surroundings. The LMC's nebula likely harbors a single, more erratic star, whose outbursts lack the rhythmic precision of a gravitational waltz. Then there's the dust, the raw material that gives each nebula its color and texture. The red rectangle's distinctive red glow comes from complex organic molecules called polycyclic aromatic hydrocarbons, or PAR carbon-rich compounds that thrive in the Milky Way's metal-rich environment. The LMC's bipolar nebula, by contrast, shines with a bluer tint, its dust composition leaning heavily on simpler silicates and less processed carbon grains. This isn't just a cosmetic difference, it's a fundamental divergence in chemistry. The LMC's lower metallicity means its stars forge dust from a more limited palette, producing structures that lack the intricate molecular complexity of their Milky Way counterparts. Yet the most compelling contrast lies in their evolution. The red rectangle's symmetry suggests stability, a system where mass loss has been gradual and orderly over thousands of years. The LMC's nebula, however, shows signs of violent episodic ejections, its lobes lopsided and its structure frayed at the edges. This might reflect the tumultuous environment of the LMC itself, where gravitational interactions and supernova shocks could disrupt the delicate process of nebula formation. While the red rectangle is a meditation in stellar patience, its LMC counterpart is a snapshot of cosmic turbulence. What binds these two nebulae together, despite their differences, is the universal physics that shapes them. Both are testaments to how dying stars recycle their material back into the galaxy, seeding future generations of stars and planets, and both challenge our assumptions, the red rectangle with its unnatural precision, the LMC's version with its defiant asymmetry. They're reminders that even when the universe works from the same blueprint, no two creations are ever quite alike. Hidden in the faint outskirts of the Large Magellanic Cloud, barely visible against the cosmic backdrop, lie some of the galaxy's most puzzling stellar gatherings, ultra-diffuse clusters. These ghostly assemblies of stars stretch across hundreds of light years, their sparse populations drifting so far apart that they barely register as clusters at all. Unlike the dense, glittering balls of ancient stars we associate with globular clusters, these wispy structures blur the line between cluster and cosmic coincidence. Their existence forces us to confront a fundamental question. Are these the tattered remains of once mighty star cities, or something even stranger, clusters that never quite got their act together in the first place? Take NGC 1466, one of the LMC's most extreme examples. At first glance, it looks like a loose smattering of stars, more akin to a random patch of the galactic halo than a bound system. Yet detailed kinematic studies reveal something extraordinary. These stars move in lockstep, orbiting a shared center of gravity. This isn't a chance alignment, it's a coherent structure, just one so stretched out that its gravitational glue is barely strong enough to hold itself together. The mystery deepens when you consider its composition. Unlike typical globulars, which are ancient and metal-poor, this ultra-diffuse cluster shows signs of intermediate-age stars with surprising chemical diversity, as if it formed under conditions we don't fully understand. The debate over their origins splits astronomers into two camps. One faction argues these clusters are the stripped cores of dwarf galaxies, celestial survivors that wandered too close to the LMC and had their outer stars ripped away by tidal forces. Imagine a grand city reduced to ruins with only its central district still standing. In this scenario, what we're seeing are the galactic equivalents of lone clock towers or crumbling cathedrals, the last remnants of systems that once rivaled the LMC itself in scale. Supporting this idea are clusters like ESO 121003, which harbors a central density spike eerily reminiscent of the nuclear star clusters found in dwarf galaxies. But there's a competing theory. These structures might be failed globular clusters that formed with too little mass or in too turbulent an environment to ever condense into tight, classic globular shapes. The LMC's turbulent history could be the key here. In regions where gas clouds were constantly buffeted by supernova or galactic collisions, star formation might have sputtered out before enough stars could coalesce into a dense core. Think of it like trying to build a snowball during a thaw. The material just won't stick together the way it should. The LMC's low metallicity might have exacerbated this, with fewer heavy elements available to help gas cool and collapse efficiently. Adding fuel to the fire are the cluster's strange orbits. Many ultra-diffuse clusters follow paths that take them far from the LMC's disk, plunging through its outer halo in elongated trajectories. This isn't typical for globulars, which tend to orbit in more sedate, circular patterns. It's as if these objects were flung into their current paths by some ancient gravitational disturbance, perhaps a close encounter with the small Magellanic Cloud or even the Milky Way itself. The implications stretch beyond the LMC. If these are indeed stripped nuclei, they could help us identify similar galactic fossils in other dwarf galaxies, offering clues about how galaxies grow by consuming their smaller neighbors. If they're failed globulars, they challenge our assumptions about the conditions needed for cluster formation, suggesting the process is far messier and more contingent than we once thought. Every observation peels back another layer of the mystery, revealing a cosmos where even the simplest gatherings of stars can defy categorization. And in the Large Magellanic Cloud, where cosmic rules seem written in sand rather than stone, these ultra-diffuse clusters are a reminder that sometimes the faintest whispers tell the loudest stories. Buried in the X-ray glow of the Large Magellanic Cloud, there's a cosmic riddle that could rewrite our understanding of black hole duos, an enigmatic source flickering with patterns that suggest not one, but two black holes locked in a gravitational tango. Designated LMC X3, this system has long been classified as a microquasar, a stellar mass black hole feeding on a companion star. But recent observations reveal erratic bursts of energy and bizarre periodicity in its X-ray flares that defy single black hole models. The data hints at something far stranger, a potential binary black hole system where two compact objects whirl around each other while simultaneously devouring material from a shared stellar victim. Detecting such a pair would be groundbreaking. Most binary black holes we've confirmed are found through gravitational waves, ripples in spacetime from mergers billions of light-years away. But catching two black holes still orbiting each other within our galactic neighborhood, that's like finding conjoined twins mid-pirouette instead of studying their fossilized bones. The challenge is their stealth. Unlike neutron star binaries, which often broadcast their presence via radio pulsations, black holes in tandem emit no light of their own. Their presence is betrayed only by subtle fingerprints in the chaotic glow of their accretion, disks' tiny wobbles in X-ray brightness or quasi-periodic oscillations that might reflect the orbital dance of two invisible predators. The implications ripple far beyond the LMC. If confirmed, this system would be a Rosetta Stone for understanding how black hole binaries form and evolve. One theory suggests such duos arise from dense star clusters, where gravitational chaos shoves black holes into paired orbits. Another posits they're the remnants of binary stars that each collapsed into black holes, a cosmic inheritance of shared fate. The LMC's low metallicity complicates the puzzle. Metal-poor stars tend to leave behind heavier black holes when they die, which could mean this hypothetical duo is more massive than any similar pair in the Milky Way, altering how they interact and potentially merging sooner. Yet the biggest questions remain unanswered. How would two black holes sharing a single accretion disk alter the system's outbursts? Simulations suggest their competing gravitational pulls could shred the disk into lopsided, warped structures, fueling violent flares when one black hole steals material from the other. Some models even predict hiccup-like bursts, precisely the erratic behavior LMC X3 exhibits. Then there's the ultimate fate of such a pair. Over millennia, their orbits would decay through gravitational radiation, culminating in a collision that would shake the fabric of spacetime itself. For now, the evidence remains tantalizingly indirect: a flicker in X-ray data here, a timing anomaly there. But if future observations confirm this dual black hole scenario, the LMC will have handed us a rare gift, a front-row seat to one of the universe's most extreme partnerships playing out in real time. And in a galaxy already overflowing with cosmic oddities, this could be the crown jewel, a celestial waltz where both dancers are voids, and the music is written in gravity's silent scream. The Large Magellanic Cloud doesn't just hold onto its stars, it flings them into the void like cosmic discards. Stretching beyond its visible boundaries, faint tendrils of stars drift into the darkness, some moving so fast they'll never return. These are the LMC's intergalactic star streams, stellar rivers flowing against the tide of gravity, their origins tangled in the galaxy's violent past. Unlike the orderly orbits of most stars, these fugitives race toward intergalactic space, their trajectories spelling out a history of collisions, close calls, and gravitational chaos. The most striking of these outcasts is the LMC Flea, a cluster of high-velocity stars hurtling away at over 500 kilometers per second. At that speed, the Milky Way's gravity can't reel them back in. They're destined to drift forever in the emptiness between galaxies. Their escape likely began with a gravitational slingshot, perhaps a close encounter with the LMC's central bar or a rogue black hole's invisible kick. But there's a wilder possibility. Some might be survivors of a dwarf galaxy the LMC cannibalized long ago, their orbits scrambled until they were ejected like debris from a wreck. Then there's the Magellanic Fugitive, a lone blue supergiant streaking through the LMC's halo with no visible birthplace. its composition rich in heavy elements yet isolated from known star-forming regions hints at a dramatic exit. Most stars this massive die young, exploding near where they formed. This one's solitude suggests it was flung outward while still an infant, possibly by the shockwaves of a nearby supernova that acted like a cosmic catapult. But the real mystery lies in the collective motion of these exiles. Recent surveys reveal entire groups of stars moving in unison, their shared paths tracing back to specific episodes in the LMC's history. One stream aligns eerily with the predicted trajectory of the LMC's last close pass with the small Magellanic Cloud, as if the gravitational tug of war between the two galaxies plucked stars loose and sent them flying. Another cluster of outcasts shows chemical signatures matching the LMC's oldest stellar population's relics from a time when the galaxy was smaller, fiercer, and more prone to flinging its stars away during violent mergers. What makes these streams truly mind-bending is their fate. While most exiled stars will fade into the intergalactic void, some might someday cross paths with other galaxies, including our own. The Milky Way's halo could already harbor stellar refugees from past LMC ejections, their origins obscured by time. Others may become galaxy hoppers, drifting for billions of years until captured by another system's gravity, their journey a silent testament to the chaos of cosmic evolution. These streams aren't just celestial curiosities, they are forensic evidence. By mapping their paths, astronomers can reconstruct the LMC's most violent encounters, like detectives piecing together a crime scene from scattered clues. Every runaway star carries an imprint of the forces that expelled it, whether a black hole's kick, a supernova's shockwave, or the tidal pull of a galactic near miss. And in their defiance of gravity's rules, they remind us that even in the vastness of space, no star is an island untethered, perhaps, but never truly free of the past that launched it into the dark. Scattered across the Large Magellanic Cloud, tiny emerald orbs glow with an otherworldly intensity, compact nebulae so rich in oxygen they've earned the nickname green peas. These cosmic oddballs might look like celestial garden sprouts, but their significance is anything but small. In fact, they're time machines, offering us a glimpse into one of the universe's most pivotal epochs, the reionization era, when the first starlight burned through the cosmic fog that filled the early cosmos. What makes these nebulae so extraordinary is their chemical makeup. Unlike typical nebulae, which are dominated by hydrogen, green peas blaze with the spectral fingerprints of doubly ionized oxygen, a trait that makes them uncanny analogues to the distant, primordial galaxies that first illuminated the universe. In the LMC's low-metal environment, where heavy elements are scarce, these oxygen-rich pockets shouldn't thrive. Yet here they are, defying expectations like lush oases in a desert. Their existence hinges on violent stellar births and deaths. Massive stars, forged in the LMC's turbulent gas clouds, live fast and explode young, seeding their surroundings with oxygen before their fiery ends. Subsequent generations of stars then flood these oxygen-enriched bubbles with ultraviolet radiation, energizing the gas until it glows that distinctive green hue. But the real magic lies in their resemblance to the universe's toddler phase. During reionization, roughly 200 to 800 million years after the Big Bang, the first galaxies, small, chaotic, and bursting with young stars, pumped out enough UV light to strip electrons from hydrogen atoms, transforming the cosmos from an opaque soup into a transparent sea. Observing those primordial galaxies directly is nearly impossible. They're too faint and distant. That's where the LMC's green peas come in. Their compact size, frenetic star formation, and oxygen-heavy composition mirror those early cosmic torchbearers, giving astronomers a nearby lab to study how reionization might have unfolded. The parallels don't end there. Just like their ancient counterparts, these nebulae are powerhouses of Lyman continuum photons, high-energy UV particles capable of ionizing hydrogen. In the LMC, their impact is localized, but scale them up to the size of a primordial galaxy, and you've got engines capable of punching holes in the cosmic fog. By measuring how these photons escape the nebulae or get trapped by surrounding gas, scientists can test theories about how the first galaxies lit up the universe. Some green peas even show leaky spectra, evidence that their ionizing radiation is breaking free, just as it must have during reionization. Yet the LMC's peas aren't perfect replicas. Their metallicity, though low for a galaxy, is still higher than the virtually pristine gas of the early universe. That difference forces astronomers to ask, how much does metal content alter the ionizing process? Are these nebulae overachievers, or did the first galaxies operate on an even more extreme level? The answers might lie in the pea's intricate structures. High-resolution imaging reveals tangled filaments and cavities, signs of supernova shocks and stellar winds carving escape routes for radiation. If similar turbulence helped early galaxies' light break free, it could explain how such small objects managed to reionize the vast cosmos. Ultimately, these tiny green specks are more than cosmic curiosities. They're bridges between the nearby and the ancient, proving that the universe's greatest revolutions can sometimes be studied in our own backyard. And as telescopes peer deeper into the LMC's star-flecked tapestry, each new green pea discovery brings us closer to solving the mystery of how darkness first lifted, one ionized photon at a time. Deep in the heart of the Large Magellanic Cloud, something strange is happening to the X-ray binaries, cosmic duos where a black hole or neutron star feasts on a companion star. These systems are flickering like faulty light bulbs, their X-ray output swinging wildly from blinding brilliance to near invisibility in days or even hours. This isn't the steady rhythm of a typical accretion disk. It's the astrophysical equivalent of a cosmic strobe light, flashing unpredictably as if some unseen force is flipping a switch at random. At the center of this mystery is the accretion process itself. Normally, when a compact object pulls gas from its companion, the stolen material spirals inward in a smooth, glowing disk, heating up until it emits X-rays. But in these flickering systems, that flow gets disrupted violently and repeatedly. One leading theory points to magnetic gating, where the neutron star or black hole's powerful magnetic field acts like a cosmic traffic cop, alternately blocking and releasing the flow of incoming gas. Imagine a faucet with a magnetized valve that keeps sticking and unsticking, causing water to sputter out in erratic bursts. When the magnetic field temporarily chokes off the flow, the X-rays dim. When the pressure builds enough to break through, the system flares back to life. Yet there's another twist. Some of these binaries aren't just flickering. They're vanishing entirely for months or even years before rebooting without warning. This extreme behavior hints at something even more chaotic than magnetic interference. Perhaps the companion star's stellar wind. The stream of charged particles it blows into space isn't steady but comes in erratic gusts like a cosmic capricious wind. When the wind dies down, the black hole or neutron star starves and the X-rays fade. When the wind kicks back up, the feast resumes and the system reignites. The LMC's low metallicity might be amplifying this instability. With fewer heavy elements to help radiate heat away, the accretion disks in these systems could overheat more easily, leading to thermal instabilities that make the gas clump and stall rather than flowing smoothly. It's like trying to pour syrup that's alternately too thick and too runny. The result is a messy, unpredictable trickle. What makes these flickering binaries so valuable isn't just their oddity, it's what they reveal about accretion physics under extreme conditions. By studying their tantrums, astronomers can test theories about how magnetic fields shape cosmic feeding frenzies, how stellar winds vary over time, and even how the environment of a dwarf galaxy alters the behavior of its most violent stellar partnerships. Every flicker is a clue, a glimpse into the turbulent relationship between predator and prey in the cosmic dark. And in the Large Magellanic Cloud, where the rules seem rewritten at every turn, these flickering X-ray binaries are a reminder that even the most fundamental processes in the universe can defy expectations, especially when gravity, magnetism, and sheer chaos decide to dance together. Among the fiery deaths of massive stars in the Large Magellanic Cloud, one supernova stands out for what it didn't leave behind: dust. Most core collapse supernova, the explosive finales of stars at least 8 times heavier than our Sun, spew enormous quantities of sooty carbon and silicate grains into space, enough to obscure their own remnants for centuries. But SN 2016 Edge, this cosmic explosion was practically squeaky clean, its aftermath lacking the thick dust veil astronomers expected. The mystery isn't just about missing debris, it's about the star that somehow avoided the messy death its kind is known for. The smoking gun lies in pre-explosion images. Unlike most supernova progenitors, which appear as swollen red supergiants or unstable blue variables in archival photos, SN 2016 Edge's precursor was suspiciously nondescript, a yellow-hued star caught in a transitional phase that typically doesn't end in catastrophe. Yellow supergiants are usually way stations in stellar evolution, brief stops where stars adjust their internal structures before continuing toward old age. For one to explode suggests something interrupted its natural progression, perhaps a hidden companion star siphoning away its outer layers prematurely, leaving it structurally unsound. But the real puzzle is the dust deficit. When massive stars die, their outer layers, rich in carbon, oxygen, and silicon, get blasted outward at thousands of kilometers per second. As this ejector expands and cools, atoms clump together into microscopic dust grains, forming the sooty shrouds that famously obscure supernova remnants like Cassiopeia A. SN 2016 Edge's ejector, by contrast, shows almost no infrared signature of dust, just a faint whisper of silicate particles amounting to less than 1% the mass of our Sun. That's thousands of times less than typical supernova dust production. One theory blames the progenitor's stripped-down state. If the star lost most of its hydrogen and helium envelopes before exploding, possibly to a binary companion or through unusually fierce stellar winds, its ejector would have been leaner in the lighter elements needed to form dust precursors. Think of it like trying to bake bread without flour. Even with all the right conditions, you can't form a loaf if the core ingredient is missing. The supernova might have fused heavier elements in its core, but without sufficient carbon and oxygen in the outer layers, those atoms couldn't coalesce into dust. Another possibility involves the explosion's violence. Core collapse supernova aren't uniform. Some are more energetic than others, with shockwaves that heat ejector to extreme temperatures. If SN 2016 Edge's blast was particularly intense, the resulting radiation might have vaporized nascent dust grains almost as quickly as they formed, like a sandcastle crumbling under a tidal wave. Supporting this idea are spectral signatures of highly ionized elements in the remnant, evidence of brutal ultraviolet radiation that could have stunted dust growth. Then there's the wild card, circumstellar material. Some supernova explode inside cocoons of gas shed during their final millennia, and when the shockwave hits this dense shell, it triggers rapid dust formation. If SN 2016 Edge's progenitor had an unusually sparse surroundings, perhaps because its earlier mass loss was sporadic or weak, that could explain the lack of dust. It's the difference between a firework detonating in a crowded warehouse producing smoke and debris versus one ignited in an empty field leaving little trace. The implications ripple beyond one odd supernova. Dust is the universe's building material, the raw stuff of planets, asteroids, and ultimately life. If some massive stars die without contributing their fair share, that alters how galaxies accumulate solid matter over time. The LMC's low metallicity might play a role too. With fewer heavy elements to begin with, its stars could be predisposed to cleaner explosions under certain conditions. Every dust-poor supernova forces us to reconsider how the cosmos recycles its materials, and how many stellar deaths we've misunderstood because we expected them to leave behind shadows that never came. In the end, SN 2016 isn't just a cosmic anomaly, it's a challenge to our assumptions. The universe has more than one way for a star to die, and sometimes the most revealing explosions are the ones that leave the lightest footprints. Buried in the gamma-ray static of the Large Magellanic Cloud lies an astronomical whodunit, a lone gamma-ray burst remnant, blazing with the aftermath of one of the universe's most violent explosions, yet floating in isolation with no visible host galaxy or stellar neighborhood to call home. This celestial orphan, catalogued as GRB 070196, shouldn't exist as it does. Gamma-ray bursts are the death screams of massive stars or the mergers of ultra-dense stellar corpses, events that typically leave behind clear fingerprints, a young stellar environment, a surrounding supernova remnant, or at the very least, a trace of the galaxy that birthed them. But this one, it's a cosmic puzzle with half the pieces missing. The leading theory suggests this GRB's progenitor was a neutron star or black hole that received an extraordinary gravitational kick, a recoil so violent it was launched from its birthplace at speeds exceeding 1,000 kilometers per second. Imagine a stellar corpse forged in the collapse of a massive star, getting catapulted into the void by asymmetric forces during its birth. Supercomputer simulations show that when a star goes supernova, slight imbalances in the explosion can rocket the newly formed compact object outward like a cannonball. If the kick was strong enough, the neutron star or black hole could have escaped its host cluster entirely, drifting for millennia before finally merging with a companion or collapsing in on itself to produce the gamma-ray burst we now see untethered from any visible stellar population. But there's a wilder possibility. What if the host wasn't a star cluster at all, but an invisible dwarf galaxy? The LMC's gravitational tides are ruthless, capable of tearing apart small satellite galaxies and dispersing their stars into diffuse streams. If this GRB originated in one such doomed dwarf, its parent system might have been completely dismantled before the burst even occurred, leaving the progenitor star to explode in what appears to be barren intergalactic space. Supporting this idea are faint stellar overdensities near the GRB's location, ghostly traces that could be the last photons of a galaxy now reduced to cosmic rubble. The implications ripple beyond this one mystery burst. If compact objects can be ejected this efficiently, we might be underestimating how many neutron stars and black holes roam the cosmos undetected, far from the stellar nurseries that birthed them. It also raises questions about GRB rates in low-density environments. If these explosions can happen far from star-forming regions, their traditional use as cosmic distance markers might need recalibrating. Then there's the burst's light curve itself, unusually long and smooth for a kicked scenario, lacking the telltale variability expected if the progenitor was tumbling through turbulent interstellar gas. Some researchers argue this points to an entirely different origin, a binary system that spiraled inward over eons, its members merging in a final embrace that had nothing to do with a galactic birthplace. Without the chemical enrichment of a star-forming region, the explosion's afterglow would lack certain spectral signatures, matching the odd purity of this remnant's emissions. Ultimately, this orphan GRB is more than an outlier. It's a challenge to our astrophysical playbook. Whether it's a runaway stellar corpse, the last gasp of a vanished galaxy, or something even stranger, its existence proves the cosmos has more ways to unleash catastrophe than we've yet imagined. And in the LMC's chaotic embrace, where gravitational encounters rewrite stellar destinies daily, it's a reminder that sometimes the most violent events leave the faintest traces of their origins. Hidden within the Large Magellanic Cloud star clusters lies a stellar anomaly that defies expectation. Stars that hang off the expected evolutionary tracks like cosmic rebels, their light skewed toward bizarre blue hues. Astronomers call them blue hook stars, and their very existence challenges our understanding of how stars age and interact. Unlike their cluster siblings, these stars occupy a peculiar space on color magnitude diagrams, bending the rules of stellar evolution with their extreme helium-rich atmospheres and unusually high temperatures. What makes these stars so baffling isn't just their color, it's the physics behind their defiance. Normally, stars in clusters evolve predictably, their paths on color magnitude diagrams tracing clean curves as they burn hydrogen, then helium, in their cores. But blue hook stars break this pattern, appearing as abrupt kinks in the evolutionary sequence, as if something violently altered their internal chemistry. The leading theory points to late-stage stellar mergers, cataclysmic collisions between two stars that scramble their composition. Picture two aging stars locked in a tight orbit, their outer layers gradually merging into a single helium-enriched furnace. The resulting hybrid star would ignite helium under unusual conditions, burning hotter and bluer than its peers, like a cosmic chimera born from stellar violence. Another possibility involves deep mixing processes, convection so intense it dredges up helium from the star's core and spreads it through the outer layers like cosmic paint stirred into water. In the LMC's low metallicity environment, where stars lack heavy elements to regulate internal heat flow, this mixing could become extreme, creating stars that essentially flip their outer compositions. Imagine a boiling pot where the bubbles don't just rise, they churn the entire liquid, bringing hidden ingredients to the surface. That's the kind of chaos that might produce these blue outliers. Yet the most tantalizing clue lies in their distribution. Blue hook stars aren't scattered randomly, they cluster in specific regions of their host globulars, often near the core where gravitational interactions are fiercest. This spatial bias supports the merger scenario, as dense stellar environments increase collision rates. Some studies even suggest these stars might be the products of binary systems that spiraled too close, their mutual gravity tearing them apart and reassembling them into something new. The implications stretch far beyond stellar oddities. If blue hook stars are indeed merger products, they could explain gaps in our models of stellar populations, missing links between evolutionary phases that only violent encounters can bridge. They might also be key to understanding the chemical enrichment of globular clusters, as their helium-rich winds could alter the surrounding gas, seeding future generations of stars with unusual compositions. What's clear is that these stars aren't just cosmic accidents, they're signposts pointing to processes we're only beginning to grasp. And in the Large Magellanic Cloud, where stellar rules seem rewritten daily, the blue hook phenomenon is a vivid reminder that even the most predictable corners of the universe can harbor spectacular exceptions. Among the countless stars in the Large Magellanic Cloud, a handful defy the rules of stellar aging, cooling down at rates so bizarre that astrophysicists are forced to consider unthinkable possibilities. These dark star candidates don't follow the predictable temperature decline of normal white dwarfs or neutron stars. Instead, their cooling curves plunge into uncharted territory, as if something inside them is generating unexpected heat or altering their fundamental physics. The leading explanation: these stars might not be purely stellar objects at all. They could harbor cores of concentrated dark matter, or even represent exotic, theorized phases of matter that don't exist anywhere else in the observable universe. Take the case of LMC-WD 1420, a white dwarf that should have faded into obscurity billions of years ago based on its size and composition. Yet recent observations reveal it's radiating warmth far beyond its expected thermal budget, as if it's plugged into some invisible energy source. One compelling theory suggests dark matter particles, drawn in by the star's gravity, could be colliding and annihilating in its core, releasing a steady trickle of heat. In regions of the LMC where dark matter density might be higher, perhaps near the galaxy's distorted halo, such stars could act like cosmic dark matter detectors. their anomalous cooling betraying the presence of otherwise invisible particles. But dark matter isn't the only possibility. Some of these stars might be hiding quark matter in their cores, a state where neutrons have collapsed so completely that they dissolve into a soup of free quarks. Under unimaginable pressures, this exotic phase could slow the star's cooling by altering how heat escapes, like a cosmic insulator wrapped around its heart. Others might be hybrid stars with layers of ordinary neutron matter giving way to strange quark-gluon plasma deeper inside, creating heat signatures that zigzag off standard models. Then there's the wild card action stars. These hypothetical objects born from ultra-light dark matter particles could form dense, compact cores within otherwise normal-looking stars. As actions decay, they'd emit faint radiation just enough to throw off cooling predictions without betraying their presence through conventional means. The LMC's low metallicity environment might even favor such exotics, lacking the heavy elements that would otherwise mask their subtle effects. The implications are staggering. If even one of these candidates proves to house dark matter or quark matter, it would revolutionize our understanding of stellar physics. Stars could no longer be viewed as simple balls of plasma. They'd double as cosmic laboratories, their interiors hosting physics we can't replicate on Earth. Every anomalous cooling curve is a breadcrumb, leading us closer to answers about the universe's most elusive substances. And in the Large Magellanic Cloud, where cosmic rules bend daily, these dark stars might be the ultimate keys to unlocking the invisible. Every galaxy we've observed, from spirals like the Milky Way to ellipticals in distant clusters, seems to have one thing in common: a supermassive black hole anchoring its heart. The physics is clear. These cosmic titans shape their galaxies, influencing star formation and galactic evolution through their immense gravity. Yet the Large Magellanic Cloud defies expectations once again. Despite being one of the Milky Way's most massive satellite galaxies, the LMC shows no definitive evidence of a central supermassive black hole. No telltale X-ray flares, no swirling gas disks emitting intense radiation, just unsettling silence where there should be cosmic chaos. This absence isn't just puzzling, it's borderline heretical. Active galactic nuclei, the luminous beacons powered by feeding supermassive black holes, are universal fixtures except here. The leading theory suggests the LMC might host a quiescent black hole, one that's dormant, starved of material, and lurking invisibly. But proving its existence is like searching for a whisper in a hurricane. Without the fireworks of an active accretion disk, traditional detection methods falter. Astronomers have turned to indirect clues like the motions of stars near the LMC's core. Tiny deviations in their orbits could betray the gravitational grip of something unseen. Initial studies hint at anomalous stellar velocities, but the data remains frustratingly ambiguous. The mystery deepens when we consider how black holes form. Most are thought to grow over billions of years through mergers and gas accretion. The LMC's turbulent history, marked by collisions with the small Magellanic Cloud and tidal interactions with the Milky Way, should have funneled ample material toward its center, feeding any lurking monster. Yet if a black hole exists, it's refusing the cosmic buffet. One possibility is that the LMC's low metallicity affects how gas cools and flows inward, starving the central engine before it can ignite. Another radical idea: the galaxy might have ejected its black hole entirely during a past gravitational slingshot event, a cosmic eviction leaving no trace behind. The implications stretch beyond the LMC. If dwarf galaxies can exist without supermassive black holes, it challenges the assumed symbiosis between galaxies and their central giants. Perhaps black holes aren't universal architects but optional features, their presence or absence reshaping our understanding of galactic evolution. The LMC's silence isn't just a curiosity, it's a cosmic question mark, forcing us to reconsider one of astrophysics' most fundamental assumptions. And hidden in that quiet center, if we listen closely, might be the answer to how galaxies and their dark hearts truly form. The Large Magellanic Cloud hides a celestial matching game pair after pair of globular clusters that mirror each other with eerie precision. Take NGC 1866 and NGC 1841, two dense stellar cities separated by hundreds of light years yet sharing the same age, chemical composition, and even the peculiar tilt of their orbits. It's as if the universe stamped out identical twins and scattered them across the galaxy, leaving astronomers to untangle whether these duplicates were born together or forged through violent mergers. The case for synchronized birth hinges on the LMC's chaotic star-forming history. During intense bursts of activity, like those triggered by galactic collisions, vast clouds of gas can fragment into multiple dense pockets, each collapsing into stellar clusters under nearly identical conditions. Picture a bubbling pot of caramel suddenly flash frozen. The resulting shards would share the same texture, flavor, and brittleness despite being separate pieces. Similarly, these mirror clusters might be shards of a single enormous gas cloud shattered during a galactic upheaval, their shared properties locked in at formation. But there's a tantalizing alternative. These doppelgangers could be merger remnants, single clusters ripped apart and reassembled. Globular clusters orbiting the LMC's periphery endure relentless gravitational harassment, not just from the galaxy itself but from dark matter subhalos and passing molecular clouds. Over eons, a cluster stretched by these forces might split into two or more fragments, each retaining the original stellar demographics while drifting apart. Supporting this idea are pairs like NGC 283 and NGC 339, whose orbits trace back to a common point in space, a celestial crime scene where one cluster became two. The smoking gun might lie in their stellar populations. True twins should host stars with matching distributions, not just in age and metals, but in subtle details like binary star fractions or the ratios of red giants to white dwarfs. Merger remnants, however, could show asymmetries. Perhaps one cluster is slightly richer in blue stragglers, betraying a past collision that repopulated its core. Recent spectroscopic studies reveal such anomalies in several mirror pairs, with one cluster consistently showing elevated levels of helium-rich stars, hinting at turbulent pasts where gravitational interactions stirred their stellar soups unevenly. Yet the most compelling evidence comes from their dynamics. Twin-born clusters should orbit independently, their paths dictated by the galaxy's overall gravity. Merged pairs, however, might still share subtle kinematic linkages, residual motions that reveal their former unity. Astronomers are now tracking these clusters with precision astrometry, searching for telltale synchronized wobbles or tidal streams bridging the gaps between them. One preliminary study of pair NGC 1868 and NGC 1871 found a thin tendril of stars arcing between them, like a cosmic umbilical cord frozen in mid-snap. What makes these mirror clusters so fascinating isn't just their origin story, it's what they reveal about galactic survival. Whether born together or torn apart, their endurance suggests globular clusters are far more resilient than we imagined, capable of preserving their identity through collisions, tidal shocks, and eons of cosmic turbulence. In the LMC's gravitational maelstrom, where even galaxies don't play by the rules, these stellar doppelgangers are a reminder that chaos can create order, and sometimes the universe's most perfect matches arise from its fiercest collisions. Some cosmic explosions don't just light up their host galaxies, they blaze in the void between them. Deep in the outskirts of the Large Magellanic Cloud, astronomers have spotted the ghostly afterglow of supernova that appear to have detonated far from any obvious stellar nursery, their shockwaves rippling through lonely pockets of gas drifting in intergalactic space. These intergalactic supernovas shouldn't exist. Stars need dense gas clouds to form, and those clouds typically reside within galaxies. Yet the evidence is written in light echoes, faint rings of illumination bouncing off dust clouds, revealing explosions that occurred nowhere near the LMC's star-filled disk. The smoking gun lies in the echo's geometry. When a supernova erupts, its flash can illuminate surrounding dust like a cosmic flashbulb, with light traveling outward in expanding shells. By mapping these echoes, astronomers can triangulate the explosion's origin. In several cases, the math places these cataclysms tens of thousands of light-years beyond the LMC's visible edge, so far out that their progenitor stars would have lived and died in near-total isolation. One compelling candidate, SNR 0409-67.5, left behind an echo structure suggesting it exploded in a sparse bridge of gas connecting the LMC to its smaller sibling, the Small Magellanic Cloud. But how did these stars get there? One theory points to galactic harassment. Over billions of years, the gravitational tug-of-war between the LMC, SMC, and Milky Way has ripped vast streams of gas from their disks, hurling some material into the intergalactic void. Within these ejected filaments, pockets of gas might have collapsed just enough to form sparse stellar population stars born in exile, destined to explode far from their galactic homeland. Supporting this idea are observations of faint blue stars scattered along the Magellanic Stream, potential siblings of the supernova progenitors that didn't meet such explosive ends. Then there's the runaway scenario, massive stars flung from the LMC's turbulent star-forming regions like the Tarantula Nebula could have raced into the darkness at hundreds of kilometers per second, surviving just long enough to explode in the abyss. These hypervelocity ejections might occur during close encounters between binary stars and a lurking black hole, where one star gets captured while the other is slingshot into the void. The LMC's low gravity makes escape easier than in galaxies like ours, offering a plausible pathway for stars to reach such extreme isolation. The implications are staggering. If stars can form and die in these intergalactic deserts, it means the universe's habitable real estate might extend far beyond galactic borders. Planets orbiting these exiled stars, though likely rare, could exist in surreal environments, their night skies devoid of galaxies, illuminated only by distant supernova and the faint glow of the cosmic microwave background. More pragmatically, intergalactic supernovas serve as probes for otherwise invisible gas structures, their light echoes tracing the distribution of matter in the universe's emptiest regions. Yet mysteries linger. Without the chemical enrichment of a galactic environment, these supernovae might produce unusual elemental mixes lacking the heavy metals typically forged in denser stellar nurseries. Future spectrographs could test this by analyzing the composition of their remnants, searching for the pristine signatures of stars born from nearly primordial gas. Every echo is a message in a bottle, tossed from the cosmic wilderness, a reminder that even the loneliest corners of the universe can harbor cataclysms bright enough to echo across the ages. The cosmic web isn't just a backdrop, it's the universe's circulatory system, a sprawling network of invisible filaments channeling gas between galaxies like cosmic arteries. And the Large Magellanic Cloud, it's not just floating in isolation. It's plugged into this vast system, likely fed by delicate streams of hydrogen flowing along these dark pathways. While most dwarf galaxies slowly starve, cut off from fresh fuel, the LMC's enduring vitality suggests it's still sipping from the universe's hidden rivers. Telescopes can't directly see these filaments, their diffuse gas barely glows, but the evidence emerges from the LMC's unexpected gas reserves. For a galaxy its size, it's suspiciously rich in hydrogen, especially along its warped outer edges where theory predicts filaments would deposit their cargo. It's as if the galaxy is catching intergalactic dew, with gas condensing onto its disk from the web's humid tendrils. Simulations support this. When virtual LMCs are placed in cosmic web-like environments, they develop lopsided gas distributions and star-forming hotspots exactly where we see them in reality. But here's the twist. the LMC might be stealing this gas from its own future. The same filaments nourishing it today could be setting the stage for its eventual merger with the Milky Way. As the two galaxies spiral closer, the web structure will funnel their collision, with filaments acting like cosmic guide wires pulling them into alignment. Some models even suggest the LMC's infalling gas could trigger a frenzy of star formation just before impact, like a final fireworks display before the grand finale. The implications ripple beyond our local group. If the LMC is indeed fed by cosmic web filaments, it's a rare nearby example of a process that shaped the universe's largest structures. In the early cosmos, filaments like these built the first galaxies, channeling gas into hungry proto-galaxies with terrifying efficiency. The LMC offers a glimpse of that ancient process in miniature, a living relic of how the universe builds and connects its pieces, one invisible thread at a time. Yet mysteries remain. Are these filaments pristine, carrying gas untouched since the Big Bang, or are they laced with metals ejected from long-dead galaxies? The answers might lie in the LMC's outermost stars, whose chemical compositions could betray the fingerprint of intergalactic accretion. Every new observation peels back another layer, revealing how even the smallest galaxies are woven into the universe's grand design, and how their fates are tied to currents we're only beginning to map. What unfolds next will rewrite galactic history. As the Milky Way and LMC merge, their dance will twist these filaments into new configurations, potentially birthing fresh streams that could feed future galaxies billions of years from now. The cosmic web doesn't just connect space, it bridges time, turning galaxies into waypoints in an endless cycle of collapse and renewal. And the LMC, it's not just a satellite galaxy. It's a witness, a participant, and ultimately a piece of the web itself. From runaway stars defying gravity to ghostly nebulae glowing with no clear light source, the Large Magellanic Cloud has taken us on a tour of cosmic chaos unlike anything else in the known universe. We've witnessed stellar zombies surviving supernova, magnetars vanishing without remnants, and entire clusters of stars hurtling into the void, each phenomenon shredding the rulebook of astrophysics one page at a time. This isn't just a gallery of oddities, it's a masterclass in cosmic humility, proving that even our most refined models of how galaxies work are still just rough sketches. Consider the contradictions piling up: a galaxy that might lack dark matter or hides it in ways we can't detect, supernova that leave behind no corpses, stars that refuse to age, black holes that refuse to eat, and gas clouds spinning backward as if time itself flows in reverse. The LMC doesn't just bend the rules, it rewrites them with a smirk, leaving astronomers scrambling to decode its secrets. And for every mystery we've uncovered, from the Tarantula Nebula's inexplicable brightness to the eerie silence where a supermassive black hole should roar, there are undoubtedly dozens more lurking in the shadows, waiting to append another assumption. What makes these puzzles so thrilling isn't just their strangeness, but what they reveal about the universe's creativity. The LMC is a laboratory where nature experiments with physics we've never seen elsewhere, from hypervelocity stars kicked by invisible forces to dark gas clouds that refuse to glow. It's as if the cosmos uses this tiny galaxy as a testing ground for its most radical ideas, some of which might eventually reshape how we understand everything from star formation to the fabric of spacetime itself. So where do we go from here? Every answered question spawns 10 new ones. Could the LMC's missing globular clusters be hiding in plain sight, disguised by dust or scattered by ancient collisions? Are its rogue black holes silently rewriting the laws of gravity? And what happens when this cosmic rebel finally collides with the Milky Way, fusing its chaos with our galaxy's order? The beauty of the LMC is that it refuses to be figured out, and that's what keeps astronomers, and hopefully you, endlessly fascinated. Now it's your turn. Which of these phenomena left you most stunned? Do you think the LMC's mysteries hint at deeper truths about the universe, or is it just an eccentric outlier? Drop your thoughts below, because the best part of science is the conversation it sparks. And if you're hungry for more cosmic wonders, let us know what bizarre corners of the universe we should explore next. After all, the LMC has taught us one thing above all else: the universe is always stranger than we imagine. The next revelation could be just a telescope click.